Good morning, everybody. Those who have not taken their breakfast, breakfast is available on the back side of this auditorium. And in a short while, we will be starting our sessions. So kindly take care of your breakfast. Thank you. Uh, Good morning, everybody. Welcome back to the second day of our symposium. And we will shortly begin session number 7. And to chair this session, we have Professor M.A. Shinoy. I would request Professor Avdhani to introduce the chair. Professor Avdhani, please.
Good morning, everyone. Welcome to day 2 of this session. I have the pleasure of introducing Dr. Professor M.A. Shinoy. He is a homegrown man. Throughout his career, he has been in ICT, formerly UDCT. He has done his bachelor's, master's, and PhD from formerly UDCT, now ICT. He has been decorated as a postdoctoral fellowship of Danish Academy, the Da Fellowship of the Danish Academy. Subsequently, he has been teaching in UDCT throughout his career. Since 1974, he has been a teacher. He has guided about 84 students, masters, PhD students, and he has got about 300 papers. He is decorated as a recognized guide of Pune University, Sholapur University, Goa University, and other universities. And he is a member of the Color Society of India. We couldn't find a better person than Professor Shinoy to chair this here. Welcome, sir. Thank you.
Good morning, everyone. I said good morning. Thank you. That is to initiate polymerization, of knowledge. So, to begin with, my regards to my mentor, Dr. Shivram. I would like to start this first session of today's program. Our first speaker is Guru Swami. He is head of the Chemical Engineering Department from IIT Mumbai. And BTech 1994, and from California, he did his further studies such as doctorate. After postdoctoral research in Max Planck Institute for Colloids and Interfaces, Germany, he has came to IIT Bombay, and presently he is a teacher in Chemical Engineering Department of IIT Mumbai. Thank you. May I present you Professor Guru Swami.
Thank you. Thank you very much, Professor Shinoy, for the kind introduction. And thank you very much for the invitation to speak at this meeting. Professor Pillai, thank you for inviting me. So just continuing from where I left off yesterday, it's an absolute pleasure for me to be here at a symposium in honor of Dr. Sivaram's 75th birthday. Notice today is also 7/5, the 7th of May. I mentioned yesterday that my first job was really as a scientist at the National Chemical Laboratory. And I joined the Polymer Science and Engineering Division, then the Polymer Chemistry Division that was headed by Dr. Sivaram. And I'm trained as a chemical engineer, but Dr. Sivaram had no problems accepting me in polymer chemistry and then continuing to let me do what I wanted. I think that those were absolutely wonderful times. It was a great way to get started on my career, and I spoke a little bit about the generous mentoring of Dr. Sivaram, and I think I want to sort of say that again. Thank you, Dr. Sivaram, because you've been very generous with your time, and that really made a big difference at the start of my career. Thank you very much. So I chose to speak about this work. So I'm currently at IIT Bombay, and I chose to speak about this work for a couple of reasons. One is that this is work that was done at NCL when I was still at the National Chemical Laboratory. This is work that was done by one of my PhD students, an absolutely outstanding student, Akash Sharma, who's currently at ULIC. He finished his PhD a few years ago and he's at ULIC now. And this is work that was done in collaboration with industry. Right? So yesterday, we had people speak about doing work which is relevant, and I think that this is some very nice science that was done which was relevant. We also had Professor Sharma speak about cellulose and the fact that we should work on cellulosic materials because these are wonderful, naturally sustainable alternatives, and I'm going to talk to you about challenges in cellulose. So, yesterday the generation of people who spoke about starting their careers doing research with very little in terms of resources. And that's wonderful, right? The power of ideas is really the most powerful thing that one has. But I want to talk to you about work that was done where we're looking at a material which is inherently complex and really trying to understand the structure of these materials. And so this is work that was done because the pioneers, the people who spoke yesterday, raised the resources to have access to equipment and infrastructure that allowed us to do work that was on complex systems and very sort of challenging systems to work on. And for that, you can't really do it without access to those resources. So I'm going to tell you about work that is, in a sense, requires advanced instrumentation, but this is really work that is then very important and relevant. So this is work that we did in collaboration with the Aditya Birla company. This Aditya Birla company is the world's largest manufacturer of regenerated cellulose fibers, and this is we talk about polymers and we talk about the fact that we are making 400 million tons per annum, but if you think about natural materials like cellulose, these are enormous, right? So cellulose is derived from plant materials. Cotton is cellulose, wood bark is cellulose, and so if you think about it, this is really the most abundant, sustainable biopolymer, right? So why don't we do more with it, right? The challenge is that cellulose is extremely difficult to work with, right? It's not a thermoplastic. You can't melt it and feed it into an extruder. It's not easy to work with. And so the way in which, one of the ways in which, of course, you can use cotton fibers by itself, but one of the ways in which you can process cellulose is to turn it into regenerated cellulose fibers. And this is it's a green material to start with, but it's a nasty process, right? So the traditional process is what's called the viscose process. So you take this bark and you dissolve it and you xanthate it essentially, and then precipitate it in sulfuric acid and some salt. So this is not a process that is particularly green, and so that's one of the reasons why you don't see. I mean, increasingly plants that do the xanthate process are not observed are not seen in the West. So the alternative, and again, I'm glad that Professor Sharma sort of alluded to this yesterday, is to move to another process where instead of using the xanthation followed by regeneration in sulfuric acid, there is a move to using a more environmentally friendly solvent. So there's N-methyl morpholine oxide, and you use a combination of N-methyl morpholine oxide and water to dissolve cellulose. That in itself is an amazing process. There's a very narrow, so it's a 3-component system. So you've got water, cellulose, and N-methyl morpholine oxide. There's a very narrow window in which you can work in, right? And if you're outside of that window, it can actually even explode on you, right? So it's a very interesting material as such to begin with. But this is something which that people now have large-scale plants, pilot to large-scale plants that use the process. This is called the lyocell process, to use N-methyl morpholine oxide water systems to process cellulose. The problem with that is that when you make fibers with viscose and lyocell, I mean, the processes in a sense are phenomenologically the same. You take wood pulp, you take bark, you dissolve it in a solvent, and you precipitate it into a non-solvent to make a fiber, right? That's the essence of both processes, but the details of the processes result in fibers that are different, right? So if you look at the viscose fibers that come out from the viscose process, so this is SEM, a scanning electron micrograph of cross sections of these. You see that macroscopically, this is at length scales of tens of microns. The cross sections of these fibers look very, very different. Now, if you take these fibers and you soak them in dye, you'll see that in the viscose, you've got a very clear core shell structure which you don't see in the lyocell. Okay? And one of the things we do observe is that lyocell fibers tend to be stiffer, a higher modulus fiber, and concomitant with that, typically if you have something that is stiffer, it also tends to be a little more brittle, and therefore it has a lower elongation to break. And one of the challenges is that if you take these kinds of fibers, and these are fibers that go into things like shirts and clothing apparel, and you put it inside the washing machine, so you're looking at wet abrasion of these systems, then materials that are made of lyocell fibers tend to fibrillate, and that's not a desirable property, right? So there are structural differences that arise. If you think about the chemistry of these materials, it's regenerated cellulose, right? But polymers tend to be more complex than just their molecular constituents. There's structure that you see at different length scales that give you the properties, and there are clearly structural differences between viscose and lyocell. So the question that we were tasked with trying to solve is, what are these structural differences? So before we get into that, let me sort of, since there are students in the audience, take you back to some very fundamental stuff, right? So very simple textbook stuff, which tells you about semicrystalline polymers, and cellulose is a semicrystalline polymer, right? And so not all polymers can crystallize. For example, polystyrene that we typically get commercially is atactic polystyrene, which means the phenyl groups are disposed on any which side of an all-trans chain. When you look at this, and therefore these are materials where you do not have the same level of molecular regularity that you would have, say, with something like isotactic polypropylene, where you have all the methyl groups on one side, disposed on one side. So what that means is disordered materials like atactic polystyrene cannot crystallize, while you need a certain level of structural regularity. And of course, that's at the stereochemical level, but of course you also need to have structural regularity in terms of the chemical units, right? So cellulose is a material which is structurally regular and can crystallize. But the thing is, in polymers, crystallinity is never 100%, right? And when I say that, that doesn't sound surprising, but let me sort of ask you this question. Suppose at atmospheric pressure, I have water at -10 Celsius, right? What is the state of that water? Right? Maybe the students can answer. Water at -10 Celsius is in what form? It's all solid, right? Is there a solid and liquid coexistence? No. How about at +10 Celsius? It's liquid, right? Is there any temperature at which you can have coexistence of liquid and solid? It's only one temperature, right? 0. At 0, you can have liquid water and you can have ice. And that comes from a thermodynamic rule called the Gibbs phase rule. Now, if I take polyethylene and I can have this material, and you can do experiments, you can do, for example, X-ray experiments to show that you have solid crystalline regions that are coexisting with amorphous regions, and you can have them at atmospheric pressure at a variety of temperatures. Now, how is that possible? Because now this is a one component system that has this coexistence, right? Now, that is not possible at equilibrium. And what that tells us, therefore, is that these kinds of semicrystalline polymers are inherently out of equilibrium systems, right? And equilibrium is good because you know exactly what you're getting every single time. But in my opinion, non-equilibrium is better because you can then control these properties, and there is nothing to constrain you to one particular structure. So non-equilibrium is, in my opinion, even more fun. Okay? But cellulosic materials, in principle, are even more complex than that, because when you look at these cellulosic materials, you have the amorphous phase, which is in equilibrium which coexists with the crystalline phase, which is glassy, right? Which means it's below the glass transition temperature. So you have these amorphous chains that are essentially motionally constrained, and there's no long-range motion in these. So if you think about a cellulose fiber, this is a semicrystalline microstructure. You start off with a fiber, and I showed you cross-sectional diameters that are of the order of microns, tens of microns in size. But if you go into these materials, then what you'll see is that you've got crystals, right? The crystals could be sort of folded crystals like this, lamellar crystals. They could be extended chain crystals. You have amorphous regions that are glassy, right? And you have voids, right? So you have this hierarchy of structures all the way from molecular unit cell length scale structures, right? So this is on the order of angstroms. These pack into lamellae. These are on the order of tens of nanometers. You've got voids which are hundreds of nanometers in size. You've got glassy regions that are disposed in between, and the entire fiber, which could in principle also have a core shell structure, which is tens of microns. So you have everything going from angstroms to tens of microns, and so you can imagine how complex that structure is, because you've got structure that's different over 4 orders of magnitude in length scale, right? And so the question is, if I'm looking at differences between viscose fibers and lyocell fibers, how does one understand these kinds of systems? And of course, you also have the aspect of orientation of these crystals, because as soon as you have crystals, it's not isotropic and you can have orientation of these systems. So the experiments that we started to do were very simple experiments, because when you have such a complex material, you want to have simple experiments that are easy to interpret. And so what we did is we took a rheometer, and this is a very advanced rheometer that allows us to measure very small forces. And what you see there in the blue is a single fiber. So my student Akash learned to get these bundles of fibers from industry. He would comb them under a microscope. He would separate out one fiber. He set up a mechanism by which he could mount this very nicely in the rheometer, and you have one single fiber that we are looking at making measurements of. And what do we do with the rheometer? You look at stress strain measurements. So the experiment that we did is, this is strain as a function of time. So you would initially continue to strain it, so there is a constant strain rate, and then you would hold it at that strain value and look at what happens in this. So I'm going to look at these two regions where I'm continuously pulling on the fiber, and then having pulled on it, I hold it to a certain extent. And what that gives you is behavior, thank you very much, that looks like this. So you have an initial region where the stress increases, and this is in the region where you're continuously pulling on it, and then in the region where you're holding it at a constant strain, you have a relaxation behavior, right? So if this were a solid, if this were a steel fiber, when you pulled it and you held it at a certain strain, the stress would be constant. But because this is this complex viscoelastic material, you have a decay of stress. Notice that this is as a function of strain. I'm plotting this as a function of time, but notice that the time again varies over many orders of magnitude, telling us that the relaxation of this complicated structure happens over a range of time scales in this system. Okay, so how do we understand this? So we took recourse to a very simple phenomenological model that's there in the literature. So you might have heard of things like the Maxwell model, where you look at viscoelasticity, you couple a spring to a dashpot. You need a slightly more complicated model, and so we coupled a spring, which this thing EC, right? That's a spring constant, and I'm going to call it EC because I'm going to show you that it relates to the crystalline stress, with an amorphous region which has a dissipative element or a dashpot or a viscous element in parallel with another spring, right? Which is EA, or the amorphous modulus. Because you have this long set of time scales, I need to have many of these in parallel. Okay. Now notice that I keep the EC the same for all, the crystal modulus. I keep the EA the same for all. The only thing that I vary is these time scales, right? So I have a relaxation spectrum of time scales that you can then model. So the model parameters I have are EC, EA, and this P of tau, which gives me the relaxation spectrum of time scales, tells me all these relaxations that I have in the system. Phenomenological model, there is no physics in it as such, it's just a model fit, okay? And so I can take that model, and there's some mathematical complexity. You have to, it's what's called an ill-posed problem, so you have to use techniques called regularization to fit it, but it's doable. And so you can get for the lyocell and for the viscose, you notice that the slope is higher for the lyocell, suggesting that it's a stiffer material. We already know that. And then you have the relaxation that is fitted using this P of tau, okay? Okay, so that's really the experiment that we want to do. And you can go ahead and do this for many fibers and average it so that you know that you're getting, so you remember that you're taking a single fiber and making measurements. So obviously you want to do this over 10, 15 fibers to make sure that you're getting consistent reproducible measurements. So the problem is not getting EC, EA, and P of tau, but the question is to ask, what does this tell us? Because I can do an experiment, I can fit a model to it. That alone doesn't tell me anything unless I can relate those model parameters to something physical. And that's something that we really were the first to do, especially for cellulose. What we were able to show is that if I do independent experiments, I've done this pulling experiments, now I'm going to do this pulling experiments inside of my X-ray diffractometer. And these are complicated measurements to do. It's an X-ray diffractometer that gives me a two-dimensional map for this. So typically when you say X-ray diffraction, you think about intensity as a function of 2 theta, but actually this is a two-dimensional X-ray measurement that you want to make because these are oriented systems. I average it out and get this I versus 2 theta, and what I can see is that I've got peaks that come from the crystal, right? Remember we talked about the fact that there is a angstrom scale crystal organization in these materials. So I look at the 002 peak, which tells me about the C-axis, tells me about where the chain is oriented. And I can see that there is a shift in the 002 peak as I pull on this, right? What does that give me? That tells me exactly what is the strain on my crystal, right? This is the peak that comes from the chain in the crystal along the chain direction, and when I pull on it, it gets stretched to a small extent, but that allows me to then calculate the strain in the crystal, right? So I know total strain I impose because that's what I do in my experiment. I know the strain on the crystal. I can calculate the strain in the amorphous regions, and since the stress is the same in the crystal and the amorphous regions, I can use this, just simple, stress divided by strain. I do this for the crystal part, I do this for the amorphous part, and from that I can then pull out the modulus in the crystal and the amorphous part, and lo and behold, what you see is that the modulus in the crystal and amorphous part is not only for lyocell and viscose, but also for other similar materials. So this is silk fibroin, which is again a semicrystalline polymer with a glassy matrix, and for PET, you can get fairly close agreement between the viscous and the amorphous parts of this. So now we know what EC and EA are in this model. We don't know what P of tau is, right? And so you look at P of tau, and remember you have this very long scale relaxation, so that means that my P of tau, the distribution of time scales, also has to be very long, right? So, and you notice it goes from really a huge range of time scales in this material, and that's the only way you can fit it. So what we did is we took the peak time scale and we looked at the temperature dependence of this peak time scale, right? And when you do that, what it tells you is that the way in which this time scale shifts has to do with something like an Arrhenius law, right? So it gives us then an activation energy or a temperature sensitivity of this relaxation time. And I can then compare that to data that's available in the literature using dielectric measurements that tell us about the temperature dependence of glassy motions. So these are glass transition motions. These are called beta motions in these systems. So remember, if I have a polymer chain, it's in the melt state, the entire chain can move, and that's the reason it's a melt. But if I go below the glass transition temperature, the whole chain can't move, but I have local relaxations, right? The temperature dependence of those local relaxations can be probed using dielectric measurements. We notice that the timescales that we get from our P of tau also then go with these same measurements, suggesting that this relaxation timescale is the timescale that comes from glassy motions in our system. And this makes sense that you would have a very large series of timescales that you require to model this. So very briefly, this is how you look at further validation. So you do this stress strain measurement, and you actually do X-ray measurements in this. Now, this is the strange bit, right? So if you look at the EC is really the slope of that stress strain curve at low strains. What does that mean? That means I'm taking the semicrystalline material and pulling on it, and the crystals are getting stretched. Now that's strange, right? Because the crystals are softer than the amorphous regions, right? If you looked at the values of EC and EA, consistently, the EA is less than the EC. So if I take a stiff material, bond it to a soft material and pull on it, you would imagine the soft material will deform. But what we are seeing is that the stiff material deforms, right? Why is that not unusual? The reason it's not unusual is the soft material also has these glassy constraints. So the soft material is not just the modulus, but this very, very slow relaxation timescales that prevents you from relaxing if you pull it fast enough, right? And fast enough is very, very slow. I mean, to really get the amorphous regions to relax, we've done those experiments. You have to pull this fiber over days, not even hours, right? So at any normal pulling speed, only the stiff crystalline material responds, and you can see that in the X-rays, right? So this is the initial 002 peak from the X-ray diffraction. As you pull on it, you see that the 002 peaks shifts to lower angles, which means the crystals are getting stretched. But then when you let it relax, right? And so that's the crystal getting stretched. And when you relax, what you're seeing is now that the amorphous peaks are shifting, and that means the strain is being transferred from the crystal to the amorphous, and we can also see that. So remember that this relaxation measurement, you've pulled it and you're holding it, right? So the crystals are all stretched out, and it's slowly pulling on the amorphous regions, and you can actually see that in the X-ray measurement, right? So complicated materials, but you really need these kind of tools to be able to get insight into this, right? So already at 25 minutes. So the story I wanted to tell you is how we can use this model to understand this difference between viscose and lyocell. I think I'm not going to have time to go through all of it, but let me try and give you a gist of this, right? So we went ahead and made measurements also of what's happening in the amorphous regions, and you can do that using a combination of techniques, right? So I told you that we're looking at X-ray diffraction, but you're looking at 2D diffraction. These are highly oriented crystal fibers, and so the X-rays also tell you that the crystals are oriented, right? So I can take this data and I can pull out from this the orientation of the crystals. Now if I can make an optical measurement on the entire fiber, just put it under the microscope and measure the birefringence, the orientation in the entire fiber comes from the orientation of the crystal and the amorphous part. If I can make a measurement of the crystal part from my X-rays, and I can make a measurement of the total orientation from my microscope, I can then calculate the orientation in my amorphous part. Okay, so that's the tool that we employ. And what that allows us to do is then to look at specifically crystal orientation. So this is a parameter where the orientation is 0, FA and FC will be 0. When the orientation is high and along the crystal axis, then the orientation will be the FC and FA will go to 1. So you notice that there's high orientation in both these systems, and as you pull on this, so this is a function of strain, as you pull on this in the lyocell and the viscose, there is an increase in the in this FC and FA on stretching. So the amorphous chains get oriented, but they don't really get there is no the crystals are the ones that get stretched out. And this is the relaxation time. And what you notice is that once you pull, the crystal orientation doesn't change very much. The crystal gets stretched and oriented, right? So the orientation doesn't change, but it shrinks. The stretching shrinks. But the amorphous regions, now you see, this is strange. You've stretched it and you're holding it, but now the orientation increases faster because when the crystals are getting unstretched, they're pulling the amorphous chains, and you can see that right here, right? So one last point I wanted to make is what happens. So this is a summary of this. What happens when you do this for the wet fibers? Remember we talked about the fibrillation problem. You take this shirt and you put it in the washing machine. It comes out with frizz that you don't like. So what you see when you do this with wet fibers is that the increase in the orientation on holding is much higher for the lyocell as compared to the viscose, right? And you can go back and translate that into the relaxation time spectrum for the dry and the wet states. This is for the lyocell materials. This is for the viscose materials. Notice that we start off in the dry state with this bimodal distribution. What does this tell us? This tells us that this cellulose, the glassy regions in the cellulose, have this distribution of relaxation timescales, including some relatively slow time, fast motions, and these are very, very slow motions, very large timescales, very slow motions. And when you wet it, these slow motions get plasticized, right? So the water, cellulose is not really, water is not a solvent for it, but the water will slightly wet it, and that water goes into these regions and plasticizes them, and therefore there's no slow motions here, right? But notice the difference, right? So for the lyocell, you've got these values going all the way to 10 to the 7. Here, these are, not as constrained. They go to about 10 to the 6. But when you wet it, this completely comes back out as compared to what you see for the viscose. So what this tells us is that the connectivity between the crystals through the amorphous phase is very, very different from the lyocell and the viscose. And so even though, in principle they're the same material, the chemistry is the same, you just have cellulosic fibers, the process by which you make these fibers makes a big difference to the microstructure. And for the polymers, properties are not just the chemical structure, it's also the microstructure, and you need these kinds of tools to determine it, right? With that, I'll stop here. So hopefully what I've been able to convince you is that you have this very simple minimal model, EC, EA, and P of tau, and that's all you need to describe this very complex structure as far as the mechanical relaxations are concerned. And we can actually interpret these model parameters in terms of microstructure, and that makes a huge difference because you really have a much deeper insight into this. And that allows us to tweeze out differences between the microstructure of the lyocell and the viscose. And in principle, it gives us ideas about how you can redesign your processing so that you can get properties of lyocell fibers that match what you get with the traditional viscose fibers. Right? With that, I'd like to stop here, and thank you very much for your attention. But I think the next speaker is using the same laptop. Okay. So
presentation is in progress. Let me introduce Professor Nikhil Singh. Professor Nikhil was first was a researcher, and then he became a teacher, and that is why research and teacher. There is no pointer? Yeah, there is. I think there is a pointer. He will give it. So, with initial studies in Kolkata, he is done masters from Kharagpur, IIT, and did his PhD from IIT Mumbai. After that, he went to several places for a postdoctoral studies and other research programs, and then he came to IIT Kharagpur with specialization in rubber technology. So, friends, let me, Dr. Nikhil.
Yeah, thank you, Professor Senoy, and for a kind introduction. And very good morning to all of you. My talk today is new class of waterborne epoxy-based fluorescent adhesive by raft-mediated emulsion polymerization using Pisha technique. So this is, though it's, I will talk about Pisha technique and also emulsion polymerization and the preparation of different functional polymers. And also I will discuss about some of the work we are doing last few years. I will brief that work. And I would like to thank Professor Pillai and Swami University, organizers of Swami University, and for giving me an opportunity to talk in front of you. And with a very nice occasion, very important occasion of 75th birth anniversary celebration of Professor Shivram. Yeah, we are organizing 75th, and as I told you yesterday, 65th birth anniversary we celebrated in IIT Kharagpur 2011 when we were organizing one international conference. And Madam and Sir, happily they are cutting the cake. And though that was not also 4th of November, but we were, they were cutting the cake. And you can see in the behind the first student of Professor Shivram, G. Satyanarayan, who is now in Bangalore in Shilpa Chemicals, and he is standing there. And Dr. Shivram has been very excellent mentor and a very great human being and excellent motivator. As Dr. Masilkar told yesterday, that excellence in one hand and relevance in other hand. And because of his excellent collaboration with GE is established in their first R&D in Bangalore, followed by many other industries. Dow, DuPont, many other industries came to India. And as rightly Professor Masilkar told, so Dr. Shivram's excellent nurturing of polymer science made an international map of Indian polymer science in international polymer scenario. And thank you, sir, and also wish you best wishes and happy and healthy life together with Madam, so that we can see you are cutting the cakes several times. Okay, my research activity goes on. We work on different functional polymers, and we prepare them by controlled radical polymerization. I will discuss a little bit about controlled radical polymerization a little bit later, and because there are many UG students are there, they may not be knowing what do you mean by controlled radical polymerization. As Professor Swami nicely explained what is called block copolymer, random copolymer, and we are also using block copolymer. So I will also explain a little bit about controlled radical polymerization. We are using different functional polymers for cell filling, shape memory, multifunctional coatings, as well as specialty elastomer applications like self-fillable elastomers, which can be used for example, tire application. We have a project with Imprint project in collaboration with Seattle. We are working on this. We are also working on smart and functional polymer gels, which are used for, we have explored this for muscle mimicking materials, contact lenses, and cancer therapy, especially by using glycopolymers, and drug delivery using glycopolymers as well as polydeuterans. And this we collaborated with School of Medical Science and Technology in our institute. We also do collaboration with other groups. I will also a little bit talk about green and sustainable chemistry and process we are using in polymers. For example, I'll give you an example. We are preparing thermoplastic elastomers by using myrcene or bioresourced monomers, ionic liquid as designer solvent, or emulsion polymerization even using by ultrasonic process, which we are collaborating with in the SPARK project with University of Melbourne. Even though Professor Shivram was there just before the pandemic, 2020, just before the pandemic in February. That was the last international conference we had held in IIT Kharagpur. And Professor Shivram and Nikos Hadjikitis also were present in that conference. Okay, about self-filling polymer, and since materials, they are always under stress and strain, like we are human being. So they undergo crack generation, micro crack generation, or damages. And in that case, so it will be nice, the people are working on different self-filling mechanism, how to prepare self-fillable polymers. Normally there are two mechanisms are used, extringing process and intringing process. Extringing process first came, that was very nicely elaborated by White et al. In the first paper in Nature, and they are micro encapsulation or microvascular approach. The problem with this process is very nicely used. They used Graph's catalyst, and the problem with this, the multiple healing is not possible. So that's why people are using nowadays intringing process based on dynamic covalent bond. Dynamic covalent bond like Diels-Schneider chemistry. I'm sorry, this is not working. So Diels-Schneider chemistry. Let me see. No, it's not working, I think. Oh, okay. Pointer, yeah, okay, I got it. So this is dynamic covalent conjugation, either Diels-Schneider reaction, or this is supramolecular type coordination bonding, or imine bonding, or boronic ester bonding, like Professor Brent, they are working on this, or disulfide linkages, hydrogen bonding, and different mechanisms they use for getting this self-filling characteristics. And in our case, we are using different click chemistry, like Diels-Schneider chemistry, based on furfural and melamine. We have also used anthracene, I'll let you know, anthracene, indole, and we have explored not only on furfural and this melamine chemistry, diene and dienophile, and alderen chemistry. We also used first time ES-click chemistry in polymer material, and alkyne azide, very well-known chemistry, also being used in case of for preparing self-filling polymers. So these are some, in a nutshell, what we have prepared. Like, for example, we have used self-filling or shape memory material, ultra hydrophobic polyacrylates, polyurethanes, elastomers, and based on Diels-Schilder and aldrin chemistry. We have used also thiolene click chemistry to functionalize a polymer or modified conventional SBS block copolymer, self-filling ionically modified bromobutyl rubber, or disulfide linkage. We have used disulfide metathesis reaction for glycopolymer for drug delivery application, or self-filling of deuterating hydrogens. We have used this kind of mechanism. Now, just to give you an example, for example, in this case we have used raft polymerization polymethyl methacrylate, furfuryl methacrylate, and just for the undergraduate students, as you know, if you do radical polymerization by using some thermal initiator like AIBN or benzyl peroxide, you get very uncontrolled molecular weight. Suppose you are targeting for 50,000, maybe you can it can lead to 1 lakh. And also polydispersity index is very high because there are several side reactions happen. Chain termination, chain transfer. So that's why controlled radical polymerization, normally they use different additives like raft, which is trithiocarbonate or sulfur mediated material, or in ATRP they use metal chloride catalyzed with copper, or they use nitroxide mediated very stable nitroxide. So they are in equilibrium with the this free radical, active free radical, so that there is no side reaction happen. That's why it leads to very controlled molecular weight and controlled polydispersity. If you take the material, suppose in this case, now what happened? What is the advantage of using raft or ATRP? You have an oil-defined N group. Now, Professor Guru Swami was telling you can prepare block copolymer. You can prepare well-defined random or well-defined graft copolymer. You can do that by using chain extension process. Okay, so that is the advantage of using controlled radical polymerization. And in this case, particularly this furfuryl chemistry why we used, because you have this functional group which can use as diene. You have dienophile, you use bismaleimide. So there is a, at room temperature, it leads to Diels-Schilder reaction. If you heat at high temperature, it leads to retro-Diels-Schilder reaction. And you can see, suppose if you have a polymer film, you have a notch, and you can see with time, healing and cooling, this notch can be, this micro cracks or notch can be healed with time, indicating that really you have dynamic covalent conjugation. So this particular chemistry also we used in case of polyurethane system. And in polyurethane system, normally we use diol, diisocyanate. And in this case, we use normally butanediol as chain extender. In this case, instead of using butanediol, we used furfuryl roof containing diol, which led to preparation of polyurethane. And after that, after preparation of polyurethane, you can see this furfuryl group we reacted with bismaleimide having POS material. POS material we have used because it gives high thermal stability, and also it gives very high hydrophobicity. So if you want to prepare some hydrophobic surfaces, you can tag this POS material. So you have used malimide, POS functionalized malimide, and then you can see that the reaction is happening. And we could see by DSC, by that heating and cooling curve, they are dynamic in nature. And interestingly, you can see this particular material, I didn't show in details about this. So you have a scratch like this, and if you heat and cool, you can see completely healed. Your polyurethane, when you start it without putting POS, hydrophilicity or this water contact angle, you can see only 84 degree, but it led to, after modification of POS material, you get water contact angle 141. Whereas you can see in case of lotus leaf, normally you have, which is self-cleaning in nature, is get ultra hydrophobicity at 150. And we could also prepare the acrylic emulsion. I'm not showing here, acrylic emulsion, which could lead to water contact angle around 140 to 150. You can see here that water droplet on the emulsion just sitting on that. If you tilt it, it will fall down, just like what happens in case of lotus leaf. So this, apart from this furfural and melamide chemistry, we have used also, this is furan melamide, we have used indole TAD, and this is also some kind of structure like bismelamide, but in this case you have nitrogen, so it is more, because the presence of nitrogen is more reactive. We have used also anthracene TAD. Anthracene has fluorescence characteristics. It also shows dynamic covalent conjugation. And we have also prepared this ES click reaction, electrophilic substitution click reaction, where your furfural molecule, not only this, it doesn't undergo Diels-Schilder reaction in this case. It undergoes electrophilic substitution reaction, giving also this dynamic covalent mechanism. So this is all about what we did. We are working on self-filling material. Also, we are working a little bit about sustainable or method or polymerization method. As Mr. Swapon yesterday told, sustainable is a very buzzword. Anyway, at least we are using some chemistry here, that ionic liquid, which has got very high thermal stability, very low VOC content, very low VOC. And so you can see here, we use this furfural methacrylate. We use particular this raft reagent. There is a significance why we have used this raft reagent. You can see it has got very high or long hydrophobic chain, which leads in some kind of nanophase separation or nanoreactor formation during the polymerization. I'm not going in details about that. Interestingly, it leads to very high degree, very high rate of polymerization, remarkably high. And even it can be done at room temperature, at 30 degrees centigrade, that polymerization might happen. And that particular material, you can see, this is the yellow material. When we add some kind of chloroform, if you add chloroform, what will happen? This ionic liquid, the chloroform, in the chloroform, the polymer will dissolve. You have ionic liquid, there will be nice phase separation. You can decant it out. You can take that ionic liquid, you can recycle several times without affecting much the conversion or efficiency of polymerization. We are also working on thermoplastic elastomer based on bio-based material. And we know styrene, butadiene, styrene block copolymer is an interesting thermoplastic elastomer, first started with Cell company. And in this case, we have used styrene. Instead of butadiene, we have used beta-myrcene. Beta-myrcene, it has got a structure like natural polyisoprene. In this case, in case of methyl group, you have another functional group, which also later on you can do different functionalization, post-polymerization modification, what we are going on doing. And so in this case, first, we prepared polystyrene, diblock polystyrene, macro raft. Then we used emulsion polymerization and used beta-myrcene. And we prepared this tri-block copolymer. And we call them SMS block copolymer. SMS in this internet or modern telephone thing, we know what is SMS. And we call them SMS block copolymer. Interestingly, it shows this stress strain curve. It is potential thermoplastic elastomer. And if you see the DSC curve, you can see two distinct TG. One is because of polymyrcene, which is coming at -63. Polystyrene, it's coming around 64. AFM shows some kind of nanostructured material. And this is the first time we did in emulsion polymerization, and with very high molecular, around 2 lakhs. There are reports of polymyrcene, like Professor Hilmer has done, but they have done anionic polymerization. And you know anionic polymerization, how difficult it do to in industrial process. So next couple of few slides I will showing on PISA polymerization, polymerization-induced polymerization, polymerization-induced self-assembly polymerization. In this case, the phenomena in situ self-assembly during the generation of blocopolymer is called polymerization-induced self-assembly polymerization. Now, conventional emulsion polymerization, we use surfactant. So when you use the surfactant, that particular emulsion polymer is very difficult for to prepare for or to use for coating or paints application, where water absorbance is a problem. In this case, in PISA polymerization, you don't need any surfactant. So it's called surfactant-free polymerization. Why? Because when you do the polymerization, normally you start with some water-soluble polymer, then when it is undergoing polymerization, that itself can act as, because of self-assembly, it can form micelle that can act as surfactant. So that's why there is no need to add surfactant. And it has got very high solid content and single pot polymerization to implement, surfactant-free emulsion polymerization, and tailoring the architecture of the block of polymer. I will show you, you can prepare different architectural polymer. And this is used for drug delivery system, stimuli-responsive block of polymer, nanosensor, and also coating applications. Though it was known a bit earlier, but Professor Steve Arms, he really has been pioneer to re-establish this chemistry, polymerization chemistry. Now, in this case, how it is done? So first of all, you have to take a water-soluble, water-soluble monomer. And typically, we can take like cationic monomer, or you can take some water-soluble polymer. And then you do raft polymerization. I think, yeah. So water-soluble block you prepared, you do the raft polymerization, so it becomes soluble. When you add this particular monomer will be water insoluble. Then during the polymerization, what will happen? They form the micelle, and the conventional emulsion polymerization happens. Now, in this case, you can really control the morphology. How you can control this P factor? And the P factor is normally when the core cell structure, you have a core diameter, you have cell diameter. The ratio of this one is called P. And this P, if it is in between half to 1, normally it leads to vesicular structure. And if it is P is this much, then it gives worm-like structure. And P is this much, then it leads to spherical structure. So all are narrated in this particular paper if you want to look at. And so in this way, you can prepare spherical or worm-like or vesicular structure. In our case, we prepared smart, polyacrylic emulsion based on new ABC type triblocopolymer via raft-mediated surfactant-free mini-emulsion polymerization. Now, in this case, it has got interesting property, anti-icing, self-cleaning, because very hydrophobic, super hydrophobic, and also antibacterial because we have ammonium salt, and we can see also it can have a very nice super hydrophobic structure. So how it was done? In this case, first we, as I told you, MTEC. So you have ammonium salt having one monomer, acrylic monomer. We did emulsion, polymerization in water. So this is water soluble. Then we added this butyl acrylate. Butyl acrylate we added because it has got very good coating film formation property. It is used for coating application. And so we get diblocopolymer. While preparing the third block, we have used polyisobonyl acrylate. Isobonyl acrylate is basically cage-like structure, cyclic structure. It has got very high hydrophobicity and also very good thermal stability. So that's why we have used IBA. And that we did with nanosilica, without nanosilica. And then we studied different properties of this particular material. And we also studied self-cleaning, anti-icing, and as well as super hydrophobic characteristics. For example, you can see this is the analysis of morphology. If you have only ABC block of polymer, you can see nice morphology here. But if you use nanosilica, you can see the nanosilica particle are adhering to the particular surface, and is giving some raspberry-like particle. And Tm, by Tm you can nicely see that this is only ABC block of polymer. It shows core cell type particle. But if you have nanosilica into this, you can see nanosilica is adhering to this core cell particle and giving this high diameter. And from the water contact angle, you can see if you are using cotton as substrate, we can see the water contact angle 153, diiodomethane contact angle 128, advancing angle is around 159. So the contact angle history is also very nice to show that really they are super hydrophobic in nature. If we put paper, it is coming 151, and in glass you can see water contact angle around 150. So this is what we also studied anti-icing thing. I am not shown here, and it can be used as a multifunctional thing. And the next thing, we try to add some fluorescent material. The objective behind it was, this was sometimes sort of in the museum, we use a lot of artifacts. So if there is a crack, and if it is, suppose they are joined, you don't know where the crack was, okay, and how to heal it. So in that case, we use some kind of fluorescent material, and in that case, we were interested to put in graphene quantum dot. And because graphene quantum dot, as you know, because of its homo-lumo transition, it shows different color depending on at what wavelength they are emitting the color. So in this case, we have used graphene quantum dot can be prepared by different methods. Yeah. This is top-down approach or bottom-up approach. Top-down approach, if you see graphene oxide, you use a lot of strong acid. No, this is not environmentally friendly method. We have used bottom-up approach. In this case, this is a poor man's graphene quantum dot, I can say. We can use citric acid, very cheap. And in hydrothermal process, 180 degrees centigrade, in 1 hour, you get graphene quantum dot having this kind of structure like this. This graphene quantum dot we used for during the polymerization of particular block of polymer. And in this case, we use vinyl pyrrolidone because so that they can have some interaction with this graphene quantum dot, and because it has got a functional group of carbonyl group and also is water soluble. So we prepared this vinyl pyridine and via raft polymerization. So we prepared micro raft, and then we did PISA polymerization because we use glycerol methacrylate, which is water insoluble or hydrophobic in nature, and you have this epoxy group. You can do a lot of post-polymerization reaction. And we prepared this. So you can see this particular one we did in presence of graphene quantum dot. This was in absence of graphene quantum dot, controlled experiment. And you can see under UV light, that is colorless. This particular block of polymer under UV light, you can see nice fluorescent color. This was characterized graphene quantum dot by usual method. I am not going in details about that. Only I can tell you that graphene quantum dot, this is citric acid, where you can see there is no sp2 carbon. But if you take graphene quantum dot, you can see there is sp2 carbon. And also, by XRD, we could see that is matching this particular XRD pattern, matching. And also, you can see citric acid, there is no lambda max at that particular wavelength, but graphene quantum dot had some wavelength, this one. So we prepared different types of block of polymer using different percentage of graphene quantum dot and also different block length of this epoxy containing monomer. And one interesting thing is that when you use graphene quantum dot, there is a retardation of the polymerization process. You can see there is a retardation of polymerization process. That's because graphene quantum dot, they have a lot of hydroxy group, phenolic hydroxy group, which normally we know retards the polymerization, radical polymerization. And that's why we see that is a conversion is less, and there is an inhibition time also. So that nicely fits the activity of graphene quantum dot. And then we got this nice structure. We can see this TEM, SEM, and in TEM structure you can see because of this pi-pi interaction, hydrogen bonding, and because if you have graphene quantum dot, normally it shows a very nice honeycomb type structure because of the interaction of graphene quantum dot. And this one then, you can see this is graphene quantum dot, without graphene quantum dot, and you can see with graphene quantum dot there is an absorbance here, and this particular material is also, you can see, is very transparent. And then we had one cup. This particular cup is broken, and this graphene containing material was used to reconstruct the cup. And you can see by under UV light, you can see where are the cracks you can see. And I can show you this. Okay, I have to go this. I can show this video. I think. What happened? This is last slide or the Okay, then I can go on this to show that. Can somebody help me to get it back to the screen? Or okay, fine. Okay, I can. Yeah, okay. I could not show this here. So where you can see the crack, yeah. So it is. You can see this is 1 kg load. The adhesive strength is so high it can easily withstand 1 kg load without breakage. And you can see here this when you're putting the UV light, you can see also that fluorescent color is there. There you can see exactly where is the crack. Okay, so in conclusion, I also try to say that we have prepared different self-healing polymers by using different mechanisms. And in this case, we have used PISA techniques to prepare ABC type of different block of polymers, whether it's graphene quantum dot or without graphene quantum dot. And I'd like to, last slide, I would like to thank especially Dr. Shivram for becoming my mentor in my scientific career, and also different funding agents, and also we have different international collaboration like Professor Voigt, Professor Andrei Peach, and Professor Jimmy Mays, with whom I had some Fulbright collaboration, and Professor Ashok Muthupandi and Professor Greg Chow. We are working on ultrasonic process. John Wilker of Purdue University, we are working on some OVTF fellowship on student with adhesive, different types of adhesive preparation, and Professor Chattaraj. So many of this DFT calculation we had to do, because to understand the mechanism, whether it's undergoing ES click, whether it's undergoing Diels-Schilder or Aldrin. So we did a lot of DFT calculation. Professor Chattaraj was very nice. He collaborated with us. Professor Mohitesh Mondal, we are collaborating with these biomedical applications. And Dr. Kavita, he started basically with furfural chemistry long back in 2008. And after that, we are working on this particular self-healing chemistry. Sarthik Samanto did a lot of work on this graphene quantum dot and PISA polymerization. And thank you very much for your kind attention.
Thank you, Dr. Nikhil. Now let us invite our next speaker, Dr. Benny George, on the dais. So we'll be listening little more about polymers towards space requirements. So Dr. Benny George is with Vikram Sarabhai Space Center after his basic studies of PhD and all in chemistry with other subjects which he has studied, and now he is dealing with polymers use especially in space requirement during his tenure at Vikram Sarabhai Center. May I invite Dr. Benny George, please.
Thank you, Professor. And let me also start by wishing a belated birthday to Professor Shivaram, and also thank my professor, Professor Rajshekharan Pillai, for inviting me to this conference. My interactions with Dr. Shivaram is very less. Maybe this is to be exact, this is the 4th time I am meeting him in person. So first it was when I joined in VSSC in 1988, there was one colleague of mine, Dr. Raghunathan Nair. He told me there is a great polymer scientist by name, because I was one of the first persons to join in VSSC with a formal training in polymer science. Then he told me that there is a great person called Shivaram. Then one day we invited by the academic and seminar committee of Vikram Sarabhai Space Center. Professor Shivaram was invited to VSSC. So I looked from a distance from him, because he was giving, I still remember a talk on polymer nanocomposites, and he explained how XRD can be used to study exfoliation of nanoclay in polymer composites. That I remember. Then second time, myself and Raghunathan Nair went to NCL for some other purpose. We met him at his office. I don't know whether he may not be remembering. Then third time was during Macro 2017. We conducted the conference at Thiruvananthapuram. I think we had one thing I noticed during that conference is that when we had the poster session is completed and other guests are enjoying the niceties of the conference. Then I saw Professor Shivaram alone walking through that hall where the posters are pasted, and he was going one after another each of the posters, though the poster session is over. We have dedicated some 2 or 2.5 hours for the poster session. It was after that. Then seeing him going through the posters, many students and many other people joined him, and that is what I call the true quality of a teacher or a professor. He is going through each poster and explaining and clarifying with each student what he has done, and he is giving then and there suggestions for their future work and so on. Okay, with this, let me move on to the topic. I was told by my professor, there will be a lot of students, and you can target your talk towards how polymer science can be useful in space research. So I have oriented my talk in that direction. So unless many of the talks which you have seen here, I may not be explaining one particular topic, but gives a bird's eye view of how polymer science and technology is important in space research, and of course some of the research which we have done towards the end of my talk. Can I have the next slide, please? Yeah, this is, as all of you may be remembering, the Indian space research started in 1963, and incidentally, that is my year of birth also. So it has started in a small village called Tumba near Trivandrum, and it was started in a church which was donated to Dr. Vikram Sarabhai by the then Bishop of Trivandrum. So from there, we started with very small sounding rockets. The rockets were carried on cycles and like that. So I have listed there what are the technologies which were developed as we went from 1963 to 2022. And if you look at the polymer science and technology, most of the developments take, I should say, in the 1980 to 1992 period, because there only we have developed most of the propellant systems, then the inhibition, insulation systems, thermal protection systems, adhesives, most of the things. But then, of course, there are productionization and modification of the systems. And finally, if you look at towards the right-hand side corner of the picture, you can see there are two things. One is the, of course, all of you might be aware from the newspaper headings that we are entering into manned space flight. And also, there was another project which is not so in the limelight, which is called reusable launch vehicle. This project was started maybe around 15 years back, but we are in between it was something like we were not going through it because of other engagements, but now it is again back in the limelight, and I will be focusing some of the materials which we are developing both for the manned space flight and also for the reusable launch vehicle towards the end of my talk. So, if you look at the polymeric materials which are being used in the space sector, particularly in the launch vehicle scenario, this is listed here right from starting from the propellant. It's a propellant binder, as you all know, is a polymer. Then there is insulation materials, inhibition. Then when you go to cryogenic propellants, we have the propellant transfer lines. That is, as you know, the cryogenic propellants consists of liquid oxygen and liquid hydrogen. And to transfer these materials from the tank to the engine, you need a material. Obviously, you can use metal, maybe metal, some of the metals like ingonal and all, but it will be very heavy and it is not flexible. So the right choice is either PEEK. Yesterday, our industrial friend, professor was telling about PEEK. And we have also been developing PEEK, and then, but unfortunately, we could not succeed with PEEK. But now the material used is polyimide, polyimide tapes, and then it is adhesively joined. That is about 2-inch width. The tape is joined by winding, and you can make it into any shape you need, and this technology is perfected, and that is used there. Similarly, coming to adhesives and sealants, there are a number of them, starting from low temperature to high temperature, high strength to low strength, contact pressure, like that. Then there are a lot of rubber products which we are using. Then in the energy systems also, a lot of polymers are used. In fact, I had 2 or 3 slides on energy systems polymer, but I has withdrawn it because yesterday Professor Shivaram was very nicely explained all those things. But I would like to inform Dr. Shivaram that though the capacity of the currently available anode and cathode materials, Professor was telling, we have crossed that limit, and something like 550 milliampere per hour lithium-ion battery we have produced, and it is already tested in the coin cell, and 50 ampere hour level battery cells we are already in the production line. But we have indigenized most of the materials there, including the cathode material. But one trouble is still with the separator material, which we are using the conventional material of polypropylene, but we are using a combination of polyethylene and polypropylene. But still, these materials are not yet available in India, it is still importing. Similarly, when you are talking about fuel cells also we have gone to, and we are realized up to 1 kilowatt, and now 100 kilowatt cell is already in the pipeline. But there also one of the major or critical elements, the proton transfer membrane, Nafion, it is still we are importing, and so I would like to inform my industry colleagues who are present here that these materials, if it can be substituted or if it can be made in India, there is a lot of value addition to it. But now we have also developed polybenzimidazole based proton exchange membranes for high temperature fuel cells. So then there is a lot of coatings, then composite materials, then thermal protection systems. These are polymers are versatile thermal protection systems, either it is as ablatives, but they can also be used as structural thermal protection systems and structural elements, wherein the concept of ceramic matrix composites will come, and I will be detailing a little bit about ceramic matrix composites. And also in the manned mission, there are a lot of materials which are required for the manned mission requirement, but almost most of these materials are again being imported. So if anybody can realize it in India, but the problem with all these materials when you are going to industry is our annual requirement will be very minimum. So that may be one of the reasons why. So I will be taking 1 or 2 examples from each of these, and finally about towards the end, around 10 or 15 minutes, I will be concentrating on the ceramic matrix composites. Then we will start with propellants. As you all know, we at ISRO made one of this polymer, what is called hydroxyl terminated polybutadiene, which is obtained by the polymerization of butadiene. But this was commercialized or produced by us ahead of the NASA early in the late 70s, and we inducted into the program even now, but there are a lot of chemistry and a lot of going into this production of this material, which is the polymerization. You should have all these elements here. I am not going to the detail, but the hydroxyl end grooves which are present there, its configuration is very important, and also the molecular weight distribution and functionality distribution are 2 other parameters. The polymerization technique developed by us and is being, we have given technology transfer to 2 industries, including Reliance, and another one is ASL, Andhra Sugars Limited. But I myself admit that it is not a very efficient process. We are getting only about 34 to 40% of the product. But again, the attempts to further increase the yield, but then we are not getting the desired properties. But this properties of this material are very important in the sense that it gives the desired mechanical properties for the solid propellant. And if the mechanical properties of the solid propellant are not good, it can, as you know, the solid motors are cast and we are firing it or using it in our rockets maybe after 5 years or 6 years or immediately in some cases also. But when they are standing, there is a possibility of this propellant to sag if the binder properties are not good enough. Similarly, if it is modulus is too high, then there is a possibility of formation of cracks. And if there is a crack inside the motor, then on firing, it will simply explode. So this is a very critical material. So that's it. Again, the importance of polymer science into it. And this polybutadiene, we are cross-linking with a diisocyanate and making it an isocyanate. So some of our friends are doing in the isocyanate chemistry, and they have produced the functional isocyanate using these monomers and also the meltable polyurethane using trimethyl propanol and hexamethylene diamine. And using a combination of these 2, they have made films which are self-healing in nature. So these are also, we are also into the research aspect of it, not related to the programmatic aspect. Again, using this functional polyurethane, we have made epoxies which are flexible. Normally, as you know, the flexibility or elongation of epoxies is very less, maybe around 4 to 7%. But in many of our applications, particularly in filament winding techniques for composite rocket motor case making, and also for development of adhesives, most of the adhesives are based on epoxies. If we can increase the flexibility of the epoxy, it will be good. So by this technique, we could increase the elongation of epoxy up to around 20%, which is very good. And based on this, we are now into the formulation making of different adhesives. So talking about adhesives, these are some of the other adhesives, specialty adhesives which we use. I would like to mention about this bottom lower one, which is called a film adhesive. These materials are being imported till now, but now we have developed the technology and the technology is now transferred to industry and then we are making it. It is the problem or the beauty with this adhesive is it is something like a tape. We just put it And then this is used for making the satellite structures, which is a honeycomb, aluminum honeycomb placed between two aluminum sheets. So this has to be bonded. And none of the conventional adhesives are accepted by the project in the sense that the properties are not meeting. One of the important property what they are looking for, so what is called the filleting. That is, the adhesive should rise to the honeycomb to a 1 or 2 mm. So whatever formulations we have tried and this work, we have been trying to make this polymer for or this adhesive for almost 10 to 15 years. But at the end we were successful now and we are now making different grades of these film adhesives. Some are with a support material in between, some without support material, and making it into the acceptable levels. And now we are getting very good properties, even better properties than the imported film adhesives. And this also we are looking for industry partners who can make it on large scale. But again, here the problem is to an industry this may not be a economically viable process in the sense that we may not be buying very huge quantities. Whatever quantities we are buying may be a few kilos or maximum a ton per year. So then coming to composites, this is again another area where polymer science and technology is playing a very important role in the field of rocketry. I will just explain this one example, which is the nozzle throat insert, which is a conventional silica phenolic composite. You know, we have been doing this research. Phenolic resins is one of the first invented polymer resins, and in fact, when we study polymer chemistry, we were taught that the first commercial polymer made is bakelite, phenolic resin, phenol formaldehyde resin. But even now, people are doing research work on phenolic resin. The reason being, this particular nozzle throat insert for the liquid engine, for the Mark III mission, you need 3 such nozzle inserts. One nozzle insert, we were importing at a cost of rupees 12 crores for one of this piece from France. And the importance of this is that through this, there's a hollow insert that the hot gases are coming, the combustion products of N2O4 and UDMH are coming. So this should have high erosion resistance and it should have very high interlaminar shear strength so that the plies will not fly off when you are subjecting into very high exhaust plumes. Then there is also a particular mechanism in this composite. What we understood is that the mechanical properties or the interlaminar shear strength and flexural strength are decreasing with respect to temperature when you heat it. But this particular composite material, when we tested, after 600 degrees, we saw an increase in the mechanical properties. So up to 600, the composite properties are reducing, and after 600, it started increasing. Then we looked at and available literature we went through, and finally, I was also one among the team. We played with simply the phenol to formaldehyde ratio and also the catalyst, and finally, though it is resol type resin, it will not cater to the resol by definition, but we made the resin and now it is used in all our missions successfully. At least some 10-15 missions have already completed, and now also we are continue to make it. This is just to say you the importance of polymer science, and also that we can also make products which are being held by monopoly by a few companies. Then coming to rubber products, we use a host of them in our launch vehicles, including the Rockwell motor case insulation, then O-rings. Talking of O-rings, we use a variety of O-rings starting from almost all sorts of rubbers. But here again, what I would like to seek the industry support is this particular O-ring, which is perfluoroelastomer based O-rings. It is commercially known by the name Calrus, trade name of DuPont, and one more company is making it Isolast. These are the only 2 companies who are making these O-rings in the world. And here also, one O-ring cost is running into lakhs and sometimes into particular shapes crores. So these are very difficult polymeric systems, and these are perfluoroelastomers. Two of the monomers are known as shown there, and the third monomer is a proprietary secret. We have, but unfortunately we could not do any experiment in these things because ethylene, tetrafluoroethylene polymerization, we cannot do it in the lab. Because TFE cannot be transported and it has to be done at the point where it is synthesized. So we are in discussions or with one of our national, I forgot that name, in Gujarat, one company is there, and recently there was a fire incident in that company that has GFL, yeah, polymers. So we are in discussions with them. We are almost at the verge of entering into a contract, but unfortunately they met with a huge accident in their TFE plants. So then this is one thing which we would again like to have. These O-rings are in demand by automobile industry also, but if somebody can make it. Then we have vibration isolators, lot of them normal things. Then we have the flex nozzle, which is as you know, the rocket's directions are controlled by flexing the nozzle. And for flexing the nozzle, we use a rubber composition, and it's called the flex seal as shown. It is a metallic shim interweaved in natural rubber. So here also we are not achieved the optimal. Can you play that movie? So we will come to know, see how the nozzle is flexed, and all this load is being driven, being taken up by this rubber. Though we are using natural rubber, even the composition, whatever we are using now, are having a lot of issues because each batch is creating us problems. So if again somebody can give us a better substitute for whatever composition we are doing, that will be welcome. I have my friend and Dr. Benny George sitting there, and he is also going to talk about rubbers. And talking about Benny George, you might have noticed while entering I was smiling because my name is announced as Benny George. I would like to correct that, at least for this audience, that I am Benny K. George. He is Benny George, and this has created a lot of confusion, particularly for this. He was coming from Cochin, I was coming from Trivandrum. Both of us arrived at the airport at the same time, and the driver came, and the phone numbers were interchanged. And so his phone number was given to as mine, and the driver called me in Pakka Marathi. I was very difficult to follow him. Then, okay, that is the fun part of it. So anyway, two of us were batchmates under Professor Pillai for the first batch of MSc Polymer Science at Mahatma Gandhi University. And when we entered yesterday in the Somaya campus, the security again started entering names. First was Dr. Shri Kumar, he entered, then I told Benny George. Then next person also Benny George. Eki coffee he sold. Okay. So I think you might have seen the flexing of the nostrils. Then so this is the interesting part, the human space flight. The most important thing is the space suit. The suit material, none of this polymer is available in India. Okay, we have been interested with the challenge of developing the suit. But fortunately, most of these materials are now available thanks to the lifting of embargo by the foreign countries. So we tried to source these raw materials, sheets as such, and tried to assemble the suit. We succeeded to some extent, but there are a lot of stringent requirements. The quality of this material, particularly with respect to CVCM, that is, what are the volatile materials coming out of it. And I am not going to the details. There is a variety of them. And yesterday I was impressed by that talk by Garda Polymers, that they are developing polyimide with some modification, which is giving an LOA of more than 90. Actually, we are looking for materials which is having an LOA of more than 60, because this outers, what is the color, that magenta or orange color thing, should be fire resistant. There are a lot of, should be have very good mechanical properties, and we are in search of a material which can be that, but it should be processable. We should make it into something like this and then stitch it and then use. Similarly, one other important, this is the only one which we have indigenized for the spacesuit material. There is a super absorbent polymer between two layers that is to absorb the body fluids of the astronaut. So we have made this acrylic-based superabsorbent polymer, which is having almost 800 times its weight of water. And then we move on to thermal protection systems. As you know, the thermal protection, it has to be protected both from internal and external heat sources, and thermal protection can be achieved by the different processes, as by insulator tiles or using an ablator. I think you people are aware of these things, so I am not going to the details. And also as hot structures, and thermal protection is not required only for high temperature, it is also required from low temperature. So when you got talk about hot structures, this is the topic I would like to say. Yesterday our gentleman, Professor Gupta or Dr. Gupta from Reliance was telling from concept to commercialization. This is something which in our terms is from concept to flight. We don't have any commercialization. If we are able to fly it, then we are hugely successful. So this is one thing which I think I am associated right from the beginning. I don't know whether I will be able to see it flying, because my term is ending in shortly, and this project may take another 4 or 5 years to complete. So, but the development will go on. That is the beauty of ISRO. This is not person dependent. There is always a system. We always have people. For example, this work, and I will come to it at the end of it. Then this is a particular material called ceramic matrix composites, where you have a ceramic as the matrix and the fiber. And I have listed the details there. The fiber can be glass fiber, carbon fiber, aramid fiber, and the matrix is very exotic material: silicon carbide, boron nitride, silicon nitride, these type of things. And you may wonder how polymer chemistry is playing a role here. It plays a role. That is what I am coming to. I would like to focus on this slide also. We have given a goal of something around 400 MPa strength at a temperature of around 2000 degrees. This is our ultimate aim. When we started, and all of the existing materials, you can see how they perform. This slide is from the literature. And then these ceramic matrix composites, almost all of the space agencies were working on it. I don't know whether they are working on it, but there is only one flight demonstration of it by the European Space Agency, which is the IEX-5 vehicle. I don't remember what is the I. It is the experimental vehicle. I forgot. I think intermediate experiment vehicle, something like that. So they flew it in 2015. None of the other space agencies, including NASA, we all know that they are all working, but whether, at least in the published literature, it is not flight tested. And these materials are being used in the highest thermal environments in reusable longitudinal wing leading edges, that is this portion, and the nose cap. These are the two areas where it is subjected to extreme temperatures. Then this type of materials, space planes or reusable launch vehicles, were hotly discussed, debated, and researched by all the spacefaring nations. But recently, the Elon Musk came and everything was in jeopardy. And he suggested and proved the reuse of the spent stage. So which people were earlier, though it was discussed, and that idea was ruled out as not economically viable, but he has shown that it is economically viable. Anyway, these are all disruptive thinkings and disruptive technologies coming in. And coming about CMC products, very simply, how this is made, we can make it by CVI process, or by polymer infiltration and pyrolysis method, or by melt infiltration. And the first step is you make the preform using your fiber, and then you make it by either CVI. As I don't know whether you are aware of, it is a gas phase reaction, but it requires very high temperature, and the equipments are hugely expensive, and it is a very slow process. Layer by layer, only the deposition of the matrix takes on the structure, and finally you'll have to subject it to machining and then give the final coating by CVI, and then your components are ready. Then another method is by using polymer infiltration and pyrolysis, where you have made the preform, and the preform is infiltrated with the polymer just like you are making any other polymer composites, and then it is subjected to pyrolysis. So all the non-carbonaceous materials will go. Then you repeat that process n times, and then finally cinder it at 1200 to 1500 degrees, you will get the ceramic matrix composites. Though this is fairly less expensive and the time consumed is less, the problem is the resultant composite will be full of porosity, and it will also affect your mechanical properties. So here comes the role of polymer in making these materials. There is a host of polymer called pre-ceramic polymers, and it's all based on the 3 or 4 elements: silicon, carbon, oxygen, boron, and nitrogen. And finally, after sintering, you should end up either with boron nitrate, silicon carbide, SiBCN, or things like that. So these are the almost all listed pre-ceramic polymers. And we have done extensive research work on these materials, and we developed some 3 or 4 pre-ceramic polymers which were then taken into further use. We will start with the polysiloxanes, then polycarboxylanes, where you have SiC as the backbone, SiO polysiloxane, and we go polyborosiloxane, we have SiOB, or you have polyborosilanes, where you have SiN, Si, and this is a play in the incorporating various atoms in the silicon polymer. And this was one of the earlier reported matrix resins for ceramic polymers. Polycarboxylane, this was invented by Ejima, a Japanese scientist, I think date back to the 70s or 80s. But the problem is that process was by a high pressure route at high temperature, 100 bar and 470 degrees. That is by the rearrangement of polydimethylase silicon. But we modified that process by introducing a small catalyst. This is the catalyst what we have developed. And by the use of this catalyst, we could reduce the polymerization temperature or the rearrangement temperature from, the pressure from nearly 100 bar to atmospheric pressure, and the temperature is reduced to 360 degrees. This process is optimized, and this is now, we have given this technology to one of the industries in Chennai, and they are manufacturing it for us. And then there are other polymers like polyborosiloxanes. I am not going into the details of how it is made and characterized, though I have all this right paucity of time. So here also we made a specific resin using this called methyl vinyl borosiloxane, which is having both silicon, oxygen, and boron in the backbone, and we have a side group of methyl and vinyl. And this particular polymer is the advantage is viscosity is very less, so you can easily use it as a infiltration resin. But the problem is, since boron is there, the oxidative stability is a little bit less when compared to polycarboxylane. But again, we have introduced other elements like titanium and zirconium. Fine, sure, I will complete it. Between this polycarboxylane, because polycarboxylane, we reacted it with zirconium acetyl acetonate, and then we could see we have polyzirconocarboxylane. That polymer was made, and this polymer was used as the infiltrating agent, and after sintering you could get the ultra high temperature ceramic phase zirconium carbide. So if you have a combination of silicon carbide and zirconium carbide, where the zirconium carbide content is more, the temperature, normally for silicon carbide based materials, the temperature limit is something like 1600 degrees. 1600 degrees SiC will melt. But if you can go to zirconium carbide, zirconium nitride, or boron carbide, boron hafnium nitride type of a thing, you can increase the temperatures to something like 2000 and 2200 degrees, which are called ultra high temperature ceramics. So you can see from the previous polymer, we have sintered it. This is the XRD, which shows the silicon carbide and the high resolution term which shows the phases of silicon carbide and zirconium carbide. And similarly, we have introduced the same chemistry, this is where we could apply whatever little bit of polymer chemistry which I have learned under the training of Professor Pillai from Mahatma Gandhi University. So we could introduce that polymer chemistry into the synthesis of these matrix resins, and we could come out with various matrix resins even up to the ultra high temperature. This is again SiBCN ceramics. This slide just shows the literature, or the only thing is it is a quite complex, laborious and seemingly expensive process. Nobody has, people have succeeded, but in gram quantities, and the processes are highly expensive. But we came out with a solution of reacting cyclotrisiloxane with boric acid, and boric acid is an important element for us in all our synthesis. And we came out with a polymer, and by changing the ratio of these things, and finally we could end, after sintering, we could end up with a pure phase which shows the only elements boron, nitrogen, carbon and silicon. So that is the SiBN ceramic we could get. And using all these matrix resins, and the beauty of system is that we used interplay of these matrix resins at different stages of polymer infiltration. So these things, by doing so, we could improve the temperature capability as well as the mechanical property of the system. Maybe you can click that video. These are various components, actual flight components we have made using these matrix resins by a combination of polymer infiltration, pyrolysis and final coating by SiC. And this is one of the critical element called wing leading edge, and this shape is reproduced in a small component here for the testing purpose, and there you can see the testing. It is subjected to 150 watts per centimeter square heat flux in air plasma, and you can see the material is cleanly withstanding. There is no erosion, there is nothing coming out of it, and this is the picture after the test. This is before the test and this is after the test, and that is the test is going on there. So we established it, we have proven it, we have done this piece of material for thermomechanical test, that is at the same time it is subjected to high temperatures and also mechanical loads, and it withstood it. We have repeated the test on the same specimen, and now we are officially into the project. So up to that we have done. So now the next phase is the final test, which is actually flight. For that, the project has to be ready, and in fact we are supposed to do one important test of this RLV in the last week at Chitradurga in Bangalore, but because of the extreme weather conditions it could not be conducted. It was supposed to be done today or tomorrow, I don't know whether it was done or not, wherein this structure will be taken to a height of around 2 kilometers by a helicopter, and it will be released. And and then the vehicle will be under self guidance, control and landing. These three aspects are being about to be tested by that test. We call it as the LEX mission. There our material is not used because no temperature is coming there, but the next is the actual flight where this material is going to be used, and we have got some patents in the fabrication of these ceramic components. So some of these materials, these polymeric systems, we have also developed into coatings. These coatings are used in thermal barrier coatings, oxidation protection coating, and then atomic oxygen resistant coatings and things like that. I am not going to the details. There also we have got some publications and some patents in this area also. Ultimately, when we coming back, this is the first slide which I have shown, where I have shown you that our goal was something around 400 degrees, 400 MBA and 2000 degrees. This is what we are very close to that, at least 350 to 400 in the mechanical properties, and temperature 1600 to 2000. And when we have the ultra high temperature matrix resins also into it, we are sure that we will exceed 2200 degrees. And we use a host of characterization techniques. This is a Raman confocal image of the cross section of the composite, you can very clearly see the red is the carbon fiber, and whatever you are seeing as green, it is, I forgot to mention that we are giving an interface coating between the fiber and the matrix, and that is either boron nitride or pyrolytic carbon. That also is seen clearly there, and what is in the blue is the ceramic matrix. So, this whole activity we have started somewhere around 2004 when the project of RLV was announced. It was started by my colleague and then boss Dr. Pakirisamy, and then I moved into it maybe around 2010, in that period 2008-10. We are also associated, and now we have, say, initially our properties we achieved was something around 73 MBA. Now we have reached the up to 1500 degrees. We have actually tested the composite, and we are retaining a property of around 400 megapascals, and we are now going to test it at 2000 degrees. The testing facilities are not available. We are establishing the facilities, and we are going to test this. This is, and now, okay, now this another young gentleman, Dr. Ranjit Devasya, is there, who is in control of these activities now. So this is continuing. So this is what from concept to commercialization, or from concept to flight. Again, the flight aspect is remaining. We have to fabricate it and then flight. That's all for me. I think I am well within time. Thank you.
Thank you, Doctor. We are ending with this session. I'll leave the floor to the organizers. Before that, let me thank organizers and Somaya Institute, as well as Polymer Society for making me chair this session. Thank you very much.
Sir, I would need you here, so just be seated. I would now request our coordinator, Dr. Vandana Jamdar, to present a memento and a shawl to Professor Shenoy. Dr. Jamdar? Yeah. Okay. Yeah, please. And the memento also. Thank you. Thank you, Dr. Jamdar. And sir, I would need your help. I will kindly invite Professor Guruswami on the stage. We would want Professor Shenoy to present you the memento and shawl. Please, bring it ahead. Yeah. Thank you, sir. And the memento also, sir. Thank you. I will now invite Professor Nikhil Singh to kindly come on the stage and request Professor Shenoy to do the presentation of the shawl and the memento as a token of remembrance from Somaya Vidya Vihar. Thank you. Thank you, sir. And now I would ask Dr. Benny K. George to come on the stage. And Professor Shenoy will present him the shawl and the memento. And the memento. Thank you very much, sir, Professor Shenoy, for your kind help. We now break for tea, and the tea break is only for 15 minutes. We would request the tea is on the hind side of the auditorium, and we will reassemble soon after 15 minutes. Thank you very much. And then we proceed to the session number 8. Yeah, your laptop is here. No, that the other speaker used, no? Yeah, he has. I think so.
Thank you.
Okay. So we are back again after the tea break, and I'm sure all of you are energized once again. So we come to the session number 8, and I would invite Professor S. Ramakrishnan to chair this session. Professor Ramakrishnan. He needs no introduction because he was already introduced yesterday, and therefore, still, I will request Dr. Dali Davis, if she is available. Okay, Sir says, no, Sir says he doesn't need any introduction, but that's fine. That makes Dali's job easy. Okay, so yes, over to you, Sir.
So, yeah, oh, no, it's okay. I'll go and sit there or I'll sit here. Yeah. So, no, I'm not the speaker. I don't need it. Yeah. So thank you very much. And it's a pleasure for me to introduce the speakers of this session. There are 3 speakers in this session. I will hold the speakers to the allotted time of 30 minutes. So please bear with me. I will stand up when there is 3 or 4 minutes left. And so it's not meant to, it's meant to ensure that we keep the time. So this session has 3 talks. One is by Professor Shri Kumar, the second Professor Anil Kumar, and the third one is Dr. Benny George, not Benny K. George, Benny George. So, without much delay, I know Professor Shri Kumar for a long time from some of the early macros. He's been a good friend and has trained a large number of students from Kerala University. And Dali, I learned, was his student as well. So thank you, Dali, for offering to introduce me, but thank you very much all the same. So Shri Kumar did his bachelor's and postgraduate degrees from Kerala University and obtained his PhD from MG University under the guidance of Professor Pillai. And since it didn't say here, so it's a pleasure. And Shri Kumar has worked on several different topics, starting from when I knew him on supported catalysis those days, and then on nonlinear optical materials and so on. So without much delay, Shri Kumar.
Thank you, Professor Ramakrishnan, for the introduction. First of all, I will thank the organizers of this symposium for inviting me here for giving a lecture, especially when Professor Shivaram attains his 75th anniversary. And I was familiar or acquainted with Professor Shivaram since 1990, when the Society for Polymer Science India was formed during that time. And the Trivandrum chapter of the Society for Polymer Science India was started during that time. And the first conference, the macro series, it was the Polymers 91. It was conducted in NCL Pune. And with Professor Pillai and his larger team, we had attended that conference. At that time, I was working as a lecturer in the University of Kerala. Then, from that time onwards, I used to meet Professor Shivaram. And in universities, in the state universities, we have one problem. No? We have to send our students for projects. Our 4th semester of MSc is completely dedicated to project. And therefore, the students have to go to some places to work in different institutes. And NCL was one of the bus centers which helped us. Every year, 13, 14 students will come to NCL. And in different divisions, especially in catalysis division, in physical chemistry division, in polymer chemistry and polymer technology division, and so on. And therefore, from those period, even before Professor Shivaram, Dr. Shivaram became the director, this help was offered to us. Dr. Mohandas was there, Dr. Joy was my senior, and similar others. My student Asha, Asha was my student at University of Kerala. Asha was PhD with Professor Ramakrishnan, and a host of others. Dr. Sri Kumar, another Sri Kumar there is in NCL. He is working on fuel cells and other systems. And likewise, we depended on NCL and different CSR laboratories in IICT Hyderabad when yesterday Lashmi Gandham was here. She also helped us a lot. And Professor Shivaram, Professor Ramakrishnan, all those were, these people were evaluators of the PhD thesis. My students, especially working on polymer supported reactions, on nonlinear optical materials, on holographic materials, photofractive polymers, etc., several different fields. And we, along with Professor Shivaram, we went to France in '95. A delegation of Indian scientists went to France in Bordeaux, in Lyon, and Paris. And in that group, Professor Kishore was there of IISc. So Shankar from IIT, he is no more. Then our IIT Bombay, I forgot his name. He was director and he got he was there. Anil Kumar Bhaumik, all those people were there, and we had a good time spending visiting different institutes in France. And from those time onwards, we were having close collaboration and interactions. And I found Professor Dr. Shivaram as a very helping person, with his humility, his down-to-earth nature. And therefore, I thank Dr. Shivaram for being an inspiration for all the polymer chemists in India. With these words, I will continue with my talk. And today, I will be presenting on very simple chemistry, nothing to do with the technology, nothing to do with industry or anything like that. Small reactions that have been conducted in a state university laboratory where we don't have much facilities. And we always depended on NCL for NMR analysis, because when I was in Cochin University, the first batch of Cochin University MSc student, Dr. Ajit Kumar and I forgot names now. He was in charge of the NMR division in NCL Pune. They had several NMR machines, especially for silicon-29 solid state NMR. We had to depend on the NCL, but they charged immensely. That's the problem. For one silicon-29 NMR, they charged 12,000 rupees. Yeah, our students may not be able to take NMR frequently. Raj Mohan, Dr. Raj Mohan was the charge of NMR division. Yeah, I am talking with on dendritic polymers. We have used these dendritic polymers as catalysts for organic reactions. When you classify the polymers, there are several classes of polymers: linear, branched, cross-linked, and the later entry is the dendritic polymers. And we have nature-inspired structures for the dendritic polymers. The perfect dendrimer we have seen shown in the first slide, first picture. Then the hyperbranched polymer, I think Professor Anil Kumar had worked on these hyperbranched polymers with Professor Ramakrishnan during his PhD days. Now, actually in polymers 94 in Baroda, Professor Ramakrishnan had presented his talk in these hyperbranched polymers. I remember that. Then dendrigraft polymers, they graft onto or graft from, etc. Different types of dendrigraft polymers can be made. And dendronized polymers, a late entry into this class. We have a long polymer chain as the core. We can use a polymer chain as the core, and on the side groups, we can
build up the dendrimer. And these are the stalwarts who had worked on dendritic polymers and dendrimers. P.J. Flory had predicted the possibility of creating dendritic polymers. Then Tomalia, Fortil, and Freshe, these people had developed the different classes of dendritic polymers or dendrimers and so on. We was fascinated with Freshe when we started working on solid phase synthesis. He was one of the pioneers in solid phase synthesis. And dendrimers have got large number of applications now, because they have been put into use in several fields, especially for drug delivery, then the biomolecular assembly and so on. Large number of applications can be envisaged for dendritic polymers. And one particular application is the use of dendritic polymers as catalysts. And this is because we can have the catalytic center either in the core, on the branching points or focal points, in the cavities, and in the periphery. And different possibilities are there. By manipulating with the functional groups, we can very easily derive the catalytic centers on different points in the dendrimers. We can have different catalytic sites incorporated with a heterogeneous type of systems on the same dendrimer. And this is our Department of Applied Chemistry at Cochin University of Science and Technology, and it is housed along with the Department of Physics. And we had started working on these dendritic polymers as catalysts during the year 2005-06. And we have developed certain organic polymer supported dendrimers, periodic mesoporous organosilica supported dendrimers, then polycarboxylane supported and homogeneous systems with different multifunctional core. And first I will deal with the solid phase or the heterogeneous organic polymer supported systems. And this was the type of work we had done during our PhD, but Benny, myself, another team during 1980s when we had done our PhD with Professor Pillai. We were dealing with solid phase synthesis, especially solid phase peptide synthesis, solid phase reagents, and so on. And during those periods, when we visited the University of Bangalore, where there was Professor Shivanandaya, he was having a synthesizer, automatic synthesizer at that time. But we didn't have any such automatic facilities. We were dealing with our hands for all synthesis. And here the importance is that the separation of the products is very easy. It's just simply filtration. Then the reaction can become driven to completion by the use of multiple steps. And therefore, we can manipulate with the process techniques when we use the solid phase strategy. And even if we say that it is a solid support, they are not strictly heterogeneous. They can imbibe a large amount of solvent and can expand. Therefore, swelling is one of the major properties of these solid supports. They are active supports. They are not passive. They are active supports. The nature of the support will control the different reactions. They have got the cooperative interactions, site isolation, or what is called the infinite dilution. Now, all those conditions can be mimicked when we do the reactions on the solid support. In the solvent state, the network will expand. And this is the classical polystyrene support that we normally use. We can make them as beads, 200 to 400 mesh size. The beads can be used. And when Professor Pillai returned from Germany, he had brought with him some 20 kilograms of cross-linked polystyrene divinyl benzene chloromethylated polymer, now called Merrifield resin. And we all use that. And also we gave that to everybody who asked the polymers. gave to Thermax Limited, Pune. And they had developed one technology for converting chloromethyl polystyrene to aminomethyl polystyrene. Now, the reaction was conducted by our group, but it was transferred free, without any royalty or without anything. They had made the aminomethyl polystyrene in large quantity. Yeah, this is simple reaction, styrene with divinyl benzene, cross-linking reaction. We will get a cross-linked polymer. It's a very controllable reaction. We can fix the degree of cross-linking. And the conversion to chloromethyl polystyrene is also very easy. It's a simple reaction. And therefore, we can get different grades of chloromethyl polystyrene with different functional group capacity, starting from 0.5 millimole per gram to higher values. And we had used some more techniques to, if you build the polymer long chain on the support, and if you have to cleave it, you have to use some simple techniques. And for that, we had used the photochemical technique. And this was a very pioneering work started with Professor Joshua, Professor Pillai's gate, PhD gate. And I had the opportunity to work with Professor Joshua for 10 years when I was a lecturer there. He was the professor in the Department of Chemistry of University of Kerala. And 2-nitrobenzyl photochemistry is known after Professor Joshua. And Professor Pillai was the student who had developed the 2-nitrobenzyl photochemistry to perfection. And using the 2-nitrobenzyl photochemistry, we can cleave the product after synthesis on the polymer support. And therefore, using the same strategy, we developed dendrimer, palm dendrimer on the solid support. And after the synthesis of the dendrimer on the solid support, we can cleave it from the solid support for analysis purpose. And definitely for analysis purpose, we have to cleave it from the solid support because the molecular weight has to be determined, the structural integrity has to be determined, whether we had any deletion sequence or truncated sequences, etc. We have to cleave it from the solid support and analyze it. By HPLC separation, and we have to purify it. And the reactions can be conducted without cleaving. On the solid support itself, we can further use it as catalyst. And this is one small system that the G3 dendrimer that can be generated on the polystyrene. And after synthesis, we can cleave, and the 2-nitrobenzyl photochemistry will work like this. It's an redox reaction. The nitro group will be reduced, and the aldehyde is obtained. And if you continue the reaction, then the cross-linking can take place. Now, we can follow the same strategy for synthesizing different polymers. And this is one of the reactions that we have utilized for making the dendronized polymer. Epichlorohydrin ring opening with butanediol, get PEC, and the PEC and gap. These are two polymers which ISRO people were using. And we have had some interaction during those days when the gap was synthesized. I had taken a Respond project for the synthesis of gap. And when you have the polyepichlorohydrin and it is attached to the polystyrene support, then the PEC attached polystyrene can be used as a polymer core for building the amino function and palm dendrimer. The PEC is converted to gap, and gap is converted to amine. Reduction of N3 can give rise to NH2 group. And we can use ethylene glycol, glycerol, or any such hydroxy compounds, multifunctional hydroxy compounds. And likewise, the synthesis continues. And the advantage of this particular method is that In the low generation itself, we can have a large number of functional groups. And because the core is a polymer, and the core has a large number of functional groups, and it can be modified to generate amino functionality at our design. With pentaerythritol, with glycerol, now we can, the core is starting with the, for PEC preparation, we can use either pentaerythritol or glycerol or ethylene glycol or sorbitol, mannitol, and so on. In order to find the structural integrity of this synthesized dendrimer, we have to cleave it and then analyze. MALDI-TOF is one of the techniques that we use for finding the molecular weight. Then we can attach metals on this, palladium catalyst or copper catalyst, etc. can be here. And when you have palladium attached to the periphery, we can also reduce the palladium complex, and you can get palladium nanoparticles embedded in the cavities of the dendrimer. And those can be used as palladium zero catalyst for Heck or Suzuki type of coupling reactions. Why it's not moving? Yeah. Here you have the palladium catalyst. And similarly, we can think of modifying the periphery. Modification can be done with some chiral moieties like proline. L-proline can be attached to the side groups, the pendant groups, and the catalyst itself will become a chiral catalyst, and therefore we can do asymmetric synthesis. Then the hyperbranched type of polymers, that the polyhydroxy, these polyether type of hyperbranch systems, which Professor Anil Kumar had done during his PhD days. Now this is in the dendritic fashion with symmetric structure. We can very easily make them on a polymer support. And different functional groups, not only amino groups, we can have hydroxyl groups or carboxyl groups, sulfonic acid groups, and so on. A large number of functional groups can be introduced on the periphery, and therefore we can have acid catalyst, we can have base catalyst, and even we can have hybrid catalyst also. Both behave acidic as well as basic. Yeah, here you see different functional groups are introduced, the azide groups on the periphery, and after we can modify them with proline. And now this is a chiral catalyst with a large number of proline groups on the surface. And also, when you have the azide, we can think of coupling it with propargyl systems, and also metals can be incorporated on this system. And this was one heterocyclic carbene, N-heterocyclic carbene system that we had synthesized, and the palladium complex of the N-heterocyclic carbene. The carbene was in the imidazoleum group was first of all synthesized by means of click reaction, the azide click reaction, and we will be able to make the palladium complex. Now using the silica support, periodic mesoporous silica as the support for synthesizing the dendritic structures. We can have different approaches for synthesizing the silica support. These are all mesoporous silica, that has been widely used, MCA41, SBA15, and so on. These were all available silica supports, and we can make them functionalized, and we will be able to synthesize the desired functional groups over the surface. And therefore, we can now think of large number of opportunities for synthesizing the functionalized periodic mesoporous organosilica. And the advantage is that they are heterogeneous, they have a large surface area, and therefore, based on the normal heterogeneous catalysis principles, we can use them as heterogeneous catalyst. We can make them in the form of pellets, we can make them in the form of beads, and therefore the heterogeneous catalytic reactions can be conducted in a flow reactor and so on. We had fabricated a similar flow reactor in our lab, and at high temperature we can do the continuous reactions. And also we can think of titanium grafted systems. And also heterocyclic carbene can also be attached as a pendant group over this silica support on the periodic mesoporous organosilica support. And similar approaches have been made for graft method, the condensation method. And we can say the triazine based dendritic system. We can grow the triazine type of molecules on this. Yeah, and then you will get a perfect dendritic type of structure with different functional groups. Here it's a sulfonic acid type of system, and carboxyl group can be introduced. Now we have a large number of carboxyl groups on the periphery of the periodic mesoporous silica. And here again the amino groups are there. Now these are all heterogeneous systems, and now coming to the homogeneous systems, we can have porphyrin rings as the core for building the dendrimer. The resorcinarine type of core can be used. Then the different polyols, pendiethyl isosorbide, fluoroglucinol, trimethylol propane, sorbitol, mannitol, inositol, glycerol, etc. Large number of such molecules can be used as core for building the dendritic system. And the advantage of using all these hydroxyl groups are just to polymerize epichlorohydrin. These are acting as initiators for the polymerization of epichlorohydrin, and you will get PEC, then convert them into azide, and then reduce to amine. And based on this, we can have these different functionalities, and this was patented. Porphyrin systems can be very easily converted to the dendritic system. Instead of the epichlorohydrin, we can use a similar monomer, the poly-bis chloromethyl oxetane. That poly-bis chloromethyl oxetane is used as a binder for explosives as well as for propellants. These people have been using this PBCMO as propellant binders. And we have one project with ISRO for making the propellant binders. And here also we can functionalize with proline. And this is calyxarine or resorcinary. Instead of porphyrin ring, we can have a completely hydrophobic system like calyxarine. It's a cavity type of molecule. Yeah, so you see the conversion of the chair form to the crown form. Now the calyxarines have different conformations, and we can functionalize the functional groups on the ring or the rim, and also in the interior. Now this type of articulation can be possible. And the polyol cord system, with isosorbide, when you have isosorbide and the epichlorohydrin taken in almost equal amount, the polymer will be a completely chiral system. we can have a chiral polymer without the attachment of any other further chiral molecule on the periphery. With trimethylol propane, with maltitol, with inositol, with fluoroglucinol, with sorbitol, and the different reactions that we have conducted during these molecules which we had synthesized. We had used the multi-component reaction strategy for synthesizing the molecules. Simplest reaction, the nominal condensation, ring opening of epoxides to get the beta amino alcohols. Then the Manich reaction, the synthesis of tetrasubstitute imidazoles as well as bis imidazoles. Now, if you use a diamine, we will be getting the bis imidazoles. The bis imidazoles are molecules which will show white fluorescence, white emission. We can play with the R group, the CH2 groups. We can start from ethylidiamine to hexamethylene, octamethylene, etc., etc. And the different heterocyclic synthesis, Suzuki coupling, Heck reaction, and so on. All carbon-carbon bond forming reactions can be conducted. And the heterocyclic synthesis continues like this. Quinoline synthesis, there are only 2 reports on the synthesis of quinolines like this with the use of amine, aldehyde, and malononitrile. It's a very neat reaction, that is, we will be able to get the product without any impurity. Any complex heterocyclic ring structure can be made by this. Now, the different reactions continues like this. When the pandemic COVID was there, we were trying to imitate the piperidine derivative for which was being used as the medicine for the tablet for easing out the symptoms. We can have a very, and one of the major reactions that we had attempted was the synthesis of warfarin. The S derivative, the isomer, the enantiomer of warfarin can be synthesized in a single step without the formation of its isomer. And normally in all the synthetic methods we will be getting with R and S warfarin, and the separation is difficult. But here in our strategy we can very easily synthesize the warfarin. In the representation for starting from aldehyde, acetone, and the coumarin, hydroxycoumarin, we can very easily synthesize the S derivative. And this is the catalyst that was used. And the advantages, high functional group capacity at the lower generation, and therefore reaction will be taking place in few seconds. Now, all the reactions can be conducted within few seconds to minutes. Numerical reaction in 1 or 2 seconds, a Manich reaction in within less than 5 seconds, and therefore all the reactions can be very easily conducted. And if you scale up, also we have done for transferring the technology to Syngene, we have scaled up these different reactions when negotiation for our transfer of the patent. All these can be conducted within few seconds to minutes. And also many reactions can be conducted in water, no toxic solvents can be used, and therefore it's a green attempt to mimic the synthesis of different heterocyclic compounds. All these dihydropyridines, all these have been used as medicinal compounds, or have been available in the market as different the amlodipine, amlodipine, which is used as a tablet for hypertension. It can be used, synthesized within a few seconds. Large quantity can be made, and therefore all these attributes are there for these different strategies. And we were happy that we had some supports from DST and UGC and Kerala Science and Technology Council, where Professor Pillai was the executive vice president for a few years, ISRO respond, and they were all contributing financially to the development of our lab. And Dr. Prathapan is our senior organic chemist. Then these are my students who had worked on the different projects. and Hiba Shibida Unnikishan. They have just submitted the thesis. And thank you. Thank you.
Thank you, Professor Sri Kumar, for keeping to time. The next speaker is Professor Anil Kumar. He's a chair professor at IIT Bombay in the Chemistry Department, Center of Excellence in Nanoelectronics, National Center for Photovoltaic Research and Education. These are multiple centers where he wears different hats. His research interests are in the area of flow chemistry, which is something he's been championing for the last almost a decade. I think he's probably one of the most well-known chemists in the area of flow chemistry in India, and his other area of interest is printable optoelectronic materials. So, and I think I'm really pleased to say that he is also started a company called Sycon Polymers India Limited, and those of you who want to know more about this can chat with him during time break. So with that, I'll leave the floor to Anil.
Thank you, Professor Ramakrishnan. It's my honor to be introduced by my guide and in a symposium to honor Professor Shivram and organized by Professor Pillai. When we were PhD student, he used to visit and we used to look up to his chemistry on Merrifield resins and how the modifications are done. So it's a special occasion for me. Today we'll share some of the recent results or recent research which we have been doing. It's into a slightly different domain. We call it process intensification. So I'll try to keep it at a very tutorial level so that all the students can understand and look into that. So we use continuous flow process for scaling up of any of the process, whether it's a polymeric process or an organic process. And we only touch those processes where there's a relevance that is immediate requirement. So that's the starting point for us. We look at the requirement, and then we identify the bottleneck, and then we say, how do you intensify that process? So during this, we make large amount of these functional materials. We work with a lot of fragrance and flavor and pharma industries. And then we make our own devices also. So we have looked into printed supercaps. We have looked into this and developed this called explosive detector, which is called Beagles. It took us 12 years from starting from the concept. In 2009, we started it. And it was a long journey. Now it's commercially available in the market with Big Tech Lab in Bangalore. And it's wonderful to see how the chemistry, when you start with an idea, then you develop the polymer, then you look at the sensing ability, then device, and then so on, and then commercial aspect when the users have to give feedback, and everything keeps changing with time. So today we look into what is process intensification. We all should know it, but somehow we forget that. We'll just quickly go into that. Then we'll look into what is continuous flow, how does that help? And then what's the relationship between two? And some examples we'll look into specifically in the domains of polymers and materials, how this is going to help us. So anything you improve in terms of a process, whether you decrease the requirement of space, you increase the throughput, you decrease the effluents, or you increase the yield, or you increase the safety. Anything which you do, it comes into, or you can call it a process intensification, and I have listed few of them and its impact on where do you do that. And now the idea as evolving with the next generation of production is, we want decentralized production. Till now, the chemical industry has been centralized where large production is at one place. Because of the challenges and because of the technology we have, and we'll look into that. Now the idea is, can you produce when and where is required? On demand, on-site synthesis, so that wherever the users are, you can produce that and move that as and when required. So let's go back to our old high school chemistry. What's a chemical reaction? Basically, you form a bond and break a bond. That's it, pretty much nothing else you do in a chemical reaction. And we all know when you break a bond, you readjust 2 electrons, and when you form a bond, you look into 2 electrons have to combine. If you can count your electrons, you can count the number of bonds you are breaking and forming. And if the event is only breaking and forming the bonds which require only relocation of the electron, and that's your translation and rotational motions. And those time scales, as we all know, should be femtosecond or sub-femtoseconds. So if a reaction has to happen, it should happen in sub-femtosecond, or it should not happen in hours and days and years. Okay? And if that is the case, every chemistry we do, it should happen at femtosecond time scale. But there's something wrong. That's where we say the chemistry should happen, and we all know it should happen here, but we do chemistry over here. That's in your 8 hours, 18 hours, or 24 hours, or 5 days, and so on and so forth. And that you wonder what's wrong between why we do this when it should happen here. And the reason for that is the technology. It's nothing to do with chemistry. At the end of the day, if you have a reaction which happens in femtosecond, and you want to make a kg of this, you can calculate the heat at femtosecond which is going to get evolved. And if you can't take that heat out, this is going to lead to the explosion. Okay? And the only way you can take heat out is from the surface. So your heat output depends on your surface to the volume ratio, and you know the utilities which you are using. So if you do the back of the envelope calculation, very simple, you know the flow rate of the utility, you know its thermal capacity, you know the surface area, and you calculate for a given system, you can find out how many joules you can extract per hour. Once you know how many joules you can extract per hour, your reaction should produce less than that. And if the reaction produces more than that, it's a runaway reaction which will lead to explosion. So because of this technological restriction of this batch, which is very poor in heat transfer and mixing, if you back calculate, all the reactions should be done in hours to days time scale. And that's the reason we do chemistry at that. So the whole idea of 100, 200 years of chemistry is how do you control the chemistry in such a way that you can scale it up, or how do you slow down the rate of the reaction so that it can be called a controlled chemistry which you can scale it up. The question one should ask, is it always speed versus control? Can we do speed and control both? And in order to do that, you need a system which will be helping you in better mixing and faster heat transfer. So that's your limiting. And the new technology, or I will not say new technology, but the new tools which are available called continuous flow tools, they allow us to do faster chemistry now, and we can do fast and ultra fast reactions. And the current state of the art allows us to do reaction in this domain, which is around 300 microseconds. Okay? So this microsecond or millisecond look very fast for you. Do remember we are still almost 9 or 12 orders away from the inherent one. Okay, so at this time when we say we can do reaction in millisecond and scale them up, it looks very, very magical that how can you do the reaction when we're doing 18 hours? We can do because the technology allows us, and maybe next generation or a generation down the line will be doing somewhere around femtosecond or picosecond, depending on what technology is available. So the moment you start doing reactions at that time scale, everything changes, your whole process changes, your process profile changes. So you can't use traditional knowledge of chemistry to start visualizing the reactions which you're doing. And since the time is limited, I'll just give you the brief couple of advantage which you get. Typically in undergraduate chemistry, we tell that you cannot do an intermolecular reaction when an intramolecular pathway is present. And that's called the rule number one in organic synthesis. But that's not a rule. That's our 200 years of observation, and observation are based on the batch technology which we are using it. But now, through flow technology, if you can improve your mixing, there are examples known where you can do an intermolecular chemistry when an intramolecular pathway is present. So all the tools and the conventional way of writing retrosynthesis, that has to change. Because if you look at your carbocation rearrangements, each rearrangement takes 6 intermediates. And the final product comes from the most thermodynamically stable carbocation. Because by the time you access the system has undergone 7 transitions or 7 rearrangements, because those are so fast, but not anymore. Using this chemistry, we can trap each intermediate, and you can open up completely new plethora of compounds which were not accessible through traditional chemistry. So what's so big deal about it? There's nothing big, continuous been there. Haber process been continuous for more than 100 years. Why go that far? All petrochemical is continuous and all your food industry is continuous. However, the chemical industry, this non-petrochemical, is not continuous. The reason for that is the volumes are very different. If you look at petrochemical and food industry, yesterday was told that 90,000 tons or something per hour the production is. Whereas you're looking at chemicals, you're looking at 10,000 tons production per year itself is a large quantity for any chemical production. So these technologies are developed from bottom up, where a process requirement is so large that people can spend lifetime in developing these technologies. So each technology is very dedicated. You'll have polypropylene, polystyrene. You can't start making today polystyrene, tomorrow polyethylene, and day after tomorrow polypropylene. You can't do that. So those technologies have been evolved with over decades and matured, and that's how the scale-up has been happened. Chemical industry, they do reactions, different day, and the volumes are still, even if they do one reaction, ibuprofen, if you look at, you're looking at 12, 15,000 tons per annum production. Still not very large. That's 1 hour, less than 1 hour production of any of the petrochemical industries. How do you now access those is what the issue was. So this is what batch technology people are using, because every day the chemistry has to change, volumes are small. And it's interesting, last 400, 500 years, nothing has changed. They're still exactly the same pots and pans, which you do in the kitchen also. Just the scales are different. They look fancier and they look better because there are more sensors and more control. And this is what happens in a batch reaction when this runs away. These are all the cases. This is the Bhopal tragedy. Remember methyl isocyanide? And if you have to do a large production of this, so the issue with batch technology is the price of the material or the price of production per unit weight decreases when the volume of production increases, because that's the economics you play with. And if you have to make a compound which is 3-step, and one of these steps require methyl isocyanide, and then you have to produce a 10,000, 20,000 liter reactor, and you want to do that reaction tomorrow, the latest starting material you can make is by midnight today. So you make large quantity of the methyl isocyanide, you store it, and hopefully morning you come and you can start your reaction, because the next batch reaction requires 12,000 liters of that. And that is required because your cost will go haywire if you don't use that scale. And if something goes wrong that night, every night nothing went wrong for decades. One night it went wrong and it just completely changed the landscape of that. So there's an inherent issues with batch technology other than the heat transfer, mass transfer. The cost scales up inversely with the volume. And then what we are saying is, can you now have tools which allow you to do continuous flow processes for low volume products, not for large volume products, which means now you have to design tools which are modular in nature, so you can do cut and paste and put them together for the requirement which you have, and the requirement can scale from milligram per hour to tons per hour production. Okay. So the continuous flow allows us and helps us to do that. Just to give you the idea, in continuous flow, you put the reagents from the one end of the tube. This is the simplest way of visualizing a continuous flow reactor, tube reactor, but we don't use tube for any of the reactions. And then they flow through the reactor, they come out of these. And this simple looking concept of entering at one point and coming out of the other point has huge implication in terms of process. What are the implications? There are no moving parts in this reactor, there are no stirrers. The mixing happens by diffusion, and the distances are you're looking at few millimeter. Okay. Heat transfer is huge because the surface area of the volume is very large. Some of the reactors in continuous flow, the spinning disk reactors, you can talk of surface area to the volume ratio of 180,000 meters square per meter cube. Typically, your batch reactors will be operating at 1 meter square per meter cube. A very good will give you 2 to 5. Your lab will have 5 to 10. As you scale up, it goes down to 1 meter square per meter cube. Imagine the reaction happening at 180,000 meters square per meter cube. How much you can enhance the rate of your reaction, or how much you just don't want to slow it down. So your batch-to-batch reproducibility is good. The most striking difference is which people don't realize, as the product travels far in the tube, fresh reagents are entering at this side. So the formed product will never see the fresh reagent which are added. And that has a huge implication if you're looking for reactions where products are more reactive than the starting material. Friedel-Crafts alkylation is one of the classical case, or all carbocationic chemistry. Second, if you're looking for crystallization, where the preformed crystal will act as a nuclei, and then all the crystals will grow on it and they'll get the lumps at the end. Or if you're looking at nanoparticle or nanofiber synthesis. So it's been documented in literature that every polymer you start synthesizing, they all grow as a nanofiber. But with time, this nanofiber now acts as a seed, and everything deposits on it and grows from it, and you get a lump at the end of the. So if you stop the reaction at few percentage conversion, you'll always land up in getting nanofiber. Those secondary nucleation is not going to be an issue in the continuous flow process. Okay. So the whole idea is, can you now think of designer molecules? Because there's a lot of interest in designer macromolecules to study structure property relationship. So can you quickly turn on and on designer materials by the day or by the hour, like in a continuous flow tap? And I'll just give you a few examples of this. Raft has been done. At every point, you can introduce a new monomer. And these are all academic curiosity, just the structure variations which you can think of this. You can make blocks, diblocks, triblocks. You can put functional group wherever is required. You can immobilize your biocatalysts on the tubes or on the chips, and you can make biopolymers or the bio-derived polymers through that. Or you can have monomers added at a different time, and you can have a sequence which you can dial in and then let it do again and again, and you get large quantity of this. Look at this, you get around 66 grams per day of a sequence, which you can dial in, and all that done by machine. So no manual intervention, and the machines keep doing it. It's basically these solid state synthesis taken into now in a different mode using that approach to that. These are all the materials, and they're all monodisperse made through that. What we have been doing, these were the academic curiosity, and I told you, we only look at what is immediately relevant to us and see how this can be helped us. So we were working in the area of this organic electronics, so we were always fascinated by these conjugated polymers. And one of the major challenges with conjugated polymer is, every time you make it, it's different. And every time, even if you buy it from the same supplier, it's a different material which you get. Because for organic electronic application, the impurity levels which you are sensitive to are in those 99.99 and 9, and after that the impurity profile is significant. And all your analytical techniques will tell you about 99% or 98 or 99%. So for a chemist, they're all pure material, but when you go into and do the device application, every batch is a different material, and that was one of the issue. So when we entered into flow, we said, can you now scale up this material? So the two schools of thought, one says, you need new materials, the right material is not there. The second school where we belong to, we believe that the material is there, the right quality is not there. So our idea was, can you make good quality materials using this? We started all the three domains, the thiophene, anilines, and the E-dots. So this is the aniline, and as I told you, you can make polyaniline nanofiber in the lab anytime, any day. You just start the reaction in any condition. Just add the monomer oxidant, stir it vigorously, stop in 2 minutes, extract that 15–10%, you'll have nanofibers. And aniline is cheapest, hydrochloric acid is cheapest, ammonium peroxide disulfide is cheap. So there's no reason to worry about 10% or 15% yield. You want kgs of this, you can't do that. Then it's gone. And this is what I have written, all the literature values, and what are the throughputs, and where we are now. We can look at the space-time yield, how multiple orders we can improve. And this is what the 6 batches at 6 different days have been made. And all of them give you the same material. And that's the beauty of this batch-to-batch reproducibility. Once you optimize your parameters and run the process, does not matter whether I turn on it or my student turns on or somebody from chemistry, not even chemistry, physics guy can come and turn on. It will still keep on churning the same. We use that, we incorporated the graphene, we made the graphene printed ink based on this. So graphene printed ink, the graphene, the percolation pathways were less. It was not very conducting that way when you make the ink. So we decided to percolate it with polyaniline, and the whole ink was developed, printed in Germany in the supercaps. And these were all the supercaps printed. And that was a project just got over before the lockdown, and let's see where the next phase of this taken. So it's a 4 collaborator. We synthesize the inks, the paper. So organic electronics is going to see the day, or is going to be important only and only when you have high quality material printed on paper substrate using the printing press across the street. Till that happens, this is going to be difficult. We keep saying organic electronics is the future, but these are the bottlenecks which need to cross. So we attempted this. So we took the paper from a German industry who made the paper. The Chemnitz University printed on paper. We made the ink, and the supercap circuits charging, discharging were made by a company in Bangalore. Then we looked into another material called poly-3-acetylthiophene, and that's where we started this icon. And it's interesting as an academician, when you look at it, you get exciting results. So this is the commercially available material, which are available from 4 different companies. We modified the process, did it through continuous flow, and whatever good or bad we do, we always get material of this quality. So very exciting that this is a wonderful material. Photovoltaics was in peak in 2013-14 based on P3HT, wonderful results. Many companies were there. So we also started the company. It took us 1.5 years to establish everything, start producing this. And you get surprises. Within 2 years, perovskites came, and the whole field abandoned the conjugated polymer and moved to perovskites. But that's part and parcel of life. So we didn't go that far. But again, after 5 years, people have come back to the conjugated polymer and again getting good traction. So our materials have been used around the world for all types of application, and everywhere we find these materials to be at multiple order better than the existing P3HT. And now we are getting calls again to scale up this material, and hopefully we'll be in a position to. We work with electrochromics. There's a 6-step synthesis all the way to the polymer, and we telescope the whole thing. So you start with the starting material, you don't have to intervene anywhere in between, and you get the final polymer in your hand. All the steps have been optimized to the best in this case. This is what close to the heart now. We realize conjugated polymers is still curiosity driven. They're very niche application, but volumes are not very large. So we looked into what can be done in terms of large volumes and where you can make an impact. So we looked into and we found emulsion polymer is one of the largest chemical industry in the country and around the globe. An issue with emulsion polymerization is it's your own black box, which means what you can do, only you can do, others can do something different. So all from monomer to polymer is a complete dynamic system which depends on your stirring speed, the humidity, the controls, the reactor, the surface volume. And if you somehow by hit and trial get one particular recipe which is working, you keep doing that. There's no way if somebody tells you that I need this acrylic emulsion at 140 nanometer, this molecular weight, and this particular, that is not possible to be given to you. There are certain molecular weight and certain range which work, and they work in their hands again and again and again. That's how the whole industry is going on. And all because of the thermodynamic stability, a lot of surfactant has been loaded. What we have been saying, can you go to the mini emulsion route or no surfactant route, dispersion route? But the issue with that route is you start with whatever size you want and you get at the same size in the polymer, but those are you're working in a kinetic domain range. Everything is in a kinetically stable state, and accessing that kinetic state at a large volumes becomes a major challenge. So we decided, can you access this large volume kinetic state using our high speed spinning disk reactors, and if you can access that kinetic state and then you activate the polymerization through that, will you be in a position to get a dial-in property of a given size and molecular weight and again of every monomer, because now your process is independent now. Its process will keep repeating, you just change the monomer or your kinetic state and you will do that. Our initial results are very encouraging. This system is what we have set it up. It looks a little complicated because we do cut and paste of every system we built up. So here's a spinning disk reactor, which is what I told you, that 180,000 meters square per meter cube. It has a spacing of 10 micron to 700 micron. I can vary the spacing, and I can vary the RPM from 1000 RPM to 8000 RPM. Imagine two liquids flowing through a space of 100 micron, where one is a stator and the other one is a rotator, and they're operating at 7000 RPM. You can pretty much mix anything at any size what you wanted. And you play around with the spacing and the flow rate and the RPM, and we are in a position to generate any of the particle of any size through this kinetic. But as soon as they come out and you leave it them for 10-15 minutes, they phase separate because they're not stabilized system. But we can generate them. And then what we did, so this is the loop over here. So it keeps this looping through this because this is churning out at 10,000 liters per hour. So we keep this looping in over here so that the whole thing is kinetically stable. And from there you take another outlet and you do in a polymerization reactor where you do the reaction. So reaction is slower than this because reaction happens in hours and that happens in milliseconds. That's the reason you keep that loop. So you built in two systems, and then we polymerize through this, and we get now particle size which you define to start with, and at the end you get the same thing. We work with various industries. We start with the process at 30, 40 milligram or microgram and scale it up all the way to 100,000 liters per day production volumes, and we generate data on this. It's not an academic curiosity. Just to give you the example, butyllithium reaction, if you have done it, we all know you can do butyllithium reaction only by dropwise addition and minus 78. That too also you need to be a seasoned chemist to do that. If you're not a seasoned chemist, they won't let you do that. And if you can do that, your company won't let you retire. 2 minutes. But this reaction now, imagine dropwise addition and minus 78, you're doing 100 kg per hour at room temperature. The reason is, we can take that much heat out. There's no magic here. It's at the end, everything has to be explained in terms of science. This is 7-meter long reactor, 400 mm diameter. You can see the car in the background. This produces 10,000 tons per annum agrochemical, which was produced by 25 tank reactors of 20,000 liters. You can imagine the size of the plant. That's replaced by this reactor. And this is a Chinese company. The reactor is from Germany, Alfeld Miprova reactor. And when the Chinese realized that this reactor can do such wonder, one product, the next day they bought the company. Now Alfeld is a Chinese company. Now they decide whom to give the reactors and how much they want to use it. You can do emulsion polymerization, which I have shown you also. They can handle high viscosity and this also. These are all the reactors which we have built up in the lab. We have state-of-the-art facility. We have all types of pump reactor downstream. We have our own NMR, IR, and we coupled everything based on the requirement and turn around in a day or two and give you the results. That's the speed at which we work. And there's nothing new. It's engineers, if you tell them, they know we know continuous. We have been doing continuous for ages. But you talk to chemists, they are not good in plumbing. Tooling is, chemists are very uncomfortable. So we got in the right spot. We learned the tooling and picked up the tool and did this. These are all the industries we have already helped or helping. More than a dozen processes developed in our lab or by the team we trained it are already in production scale. And hoping in few years, we will have a large number of production through continuous flow. And we just inaugurated one of the first center in Telangana called Center for Excellence in Flow Technology. There's a tripartite agreement between Dr. Reddy's lab, Laura's lab, sponsored University of Hyderabad and Telangana government. And I helped them in setting up all the tools. I put up my students after training, and the center was just inaugurated last week. To teach the community, earlier we used to teach industry and charge, but in the COVID lockdown, I decided I have put all my teachings on continuous flow, YouTube, free of cost. So we charge 15 lakh rupees for one industrial training. Now it's free of cost for everybody because we have done 40 trainings and we're comfortable now with this. All the lectures are available from starting all the way to the end, how you pick up the reactor, how you use the reactor, what reaction fits of which reactor. Everything we know is available in these videos. If you still don't understand, you can always email me and we'll pick it up from there. So process intensification, if you have any issue with the process or you want to set up a new process, you better go with flow. There's no point in going old. Don't look at the initial cost because that's not the way business should be looked into. Business should be looked into return on investment. Investment initial is higher, but return on investment we generally have observed from 6 to 9 months and the reactors last for 20 to 30 years. So return on investment, you do that. Don't think in batch and do in flow, you have to just do flow. If some tricks are there, it's just learning driving. You can learn it, it's not very difficult. Do not think out of the box, throw the box. These are all the students who are trained and working with us. And these are the people who use our P3HT and have done wonderful results and hope to churn out more materials and new processes. So we are very happy and hopefully chemical industries will use our process in the future. Thank you for listening to me and I'll be happy to take some questions.
Perfect timing and fantastic work. I just forgot to mention that Anil also received an appreciation for the effort that he has made, the Platinum Jubilee National Award for Application-Oriented Research from NASI RIL in 2017. Really nice to see that we've moved on to some really exciting science and technology. So with that, thanks Anil, and collect your. I'm sorry, I think we have. But I'm here. Culture of not having questions because we are running out of time. Sure, absolutely. Yeah. So now I have the last speaker of this session to invite, and that is the original Benny George, and not Benny K. George, but Benny George. And Benny George is working at the Rubber Research Institute of India in Kottayam, and he received his PhD from the Center of Polymer Science at IIT Delhi. And his research interests are in the area of natural rubber, synthetic rubber blends, vulcanization, and so on. The whole works of rubber chemistry, which is fairly complex and incredibly important. So let me invite Benny to go for his talk.
Good afternoon. Thank you for inviting me to this program, to Professor Rajasekhar Pillai, who is my professor also, okay. And greetings and belated birthday wishes to Shivaram sir. Actually, I had the privilege of traveling with Dr. Shivaram when he came to our institute in 2004 or 5, I think. And I took him from the airport to our institute. It's a 2.5 hours journey in the car without knowing that properly understanding that I am traveling with a giant in polymer science. Okay, so my presentation is on natural rubber production, processing, and recent research innovations in the field. So this is the institute. This is in Central Kerala. And the first one is the major part, or the first building we had in 1963 or so, 56 it was in 56. And then the second one we had in around 2000, and then 2005 we had a Golden Jubilee building, and that both were inaugurated by the then presidents at that time. Okay, many of the students, actually I was given a mandate of presenting it, introducing natural rubber, etc. to the student community rather than to the scientist community here. So I will be going that way. So this is a rubber plantation actually. The left figure is the rubber plantation. In 1 hectare, around 500 plants can be planted. And the plant requires around 6 to 7 years to mature before harvesting the latex. And the latex is harvested like a knife by a tapper. A 1 centimeter less than, 2 mm cut is made each in 3 days per week, And then you get around 120 to 150 ml of latex, which contains around 40 to 50 grams of dry rubber. So this is the way, and we have around 1 million hectare of land planted with this one, and majority is in Kerala, and some part of India, like in northeast, in Tripura, in Assam, etc. We have some 2 lakh hectares. Now we have a plan to increase the area of under cultivation to another 2 lakh hectares with the help of the tire industry and the Ministry of Commerce. Actually, our institute comes under Ministry of Commerce and Industry. So this is a composition of field latex. So the latex you obtain from the tree, it has this composition: rubber hydrocarbon around 30%, proteins 2, resins and lipids 1, carbohydrates and sugar 1.5%, inorganic ash part is 0.5, and majority is water. So this is the process of making a sheet. How do you, it is a colloidal liquid which is negatively charged. Therefore, we can add dilute acid, either formic acid or acetic acid. We use only organic acid because while drying, the acid should not leave in the surface. If you use sulfuric acid or any inorganic acid, the problem is that it won't evaporate during drying. So when it dries, it gets concentrated and degrade the rubber, and therefore we use only organic acid. So this is the process, like you take seaweed, dilute it, and then add acid, keep it there for coagulation and maturation, etc. And then you take it out and bale it, you put it in the sheet, and then dry in a smoke house at 60 to 70 degrees centigrade. And this is the way it is done. Like we take it in aluminum pans. It's all done by the farmers. It's done in the aluminum pan. We actually dilute it with water and add the required amount of acid to neutralize. Then it will coagulate, and after coagulation, it will be just like paneer with a softer texture. Okay, just like paneer, but paneer is much harder. This will be much softer. And then we pass it through a two-roll roll to squeeze out the excess water and come out with a sheet which is hanging there. It will be white when it contains water. And when it's dry, it will be honey colored. So the entire rubber industry is running on these things. You move on these things, you land on the plane with this, this material. And many of the insurance companies will not insure the plane if the tire is made out of natural rubber. So important, so strategic important. So in our institute, we have a feeling that, it is as strategic as chip. And it is, actually. This is how the primary processing is done in our country. Like, after primary processing, we have the NR, latex, and 70 to 85% is field latex. But the 15 to 25% is the tray laces. When you cut it out, you take it from, some will be left out, and that will be there. So that is also valuable material that we can process and convert it into technically specified rubber. And in the field latex, what we obtain from that, we use this rib smoked sheet. That is 85% of the production in our country. 12% of the latex we preserve with ammonia. Ammonia is a good antibacterial agent, and therefore it won't see if bacteria works. What happens is that carbohydrates and sugar are there. It will produce alcohol and acid, and automatically it will coagulate. So if you want to keep the latex as latex, then we have to use ammonia, 1% ammonia on the weight of the latex. If 1 kg is 1% ammonia is used in the latex, and then we centrifuge the latex because we know we have 30% these things. So if somebody in Bombay or in Delhi or in Chandigarh or in any other place to want to make a rubber, latex-based products, he will be transporting more water than the, and the rubber. So in centrifuging factories, what they do is they just reverse the concentration of the latex from 30 to 60 parts. And there should be at the end concentration, after concentration, it is 60% rubber and 40% water. And then using that, actually all the latex-based products are made, like from medical gloves, examination gloves, catheters, condoms, balloons, you name it. All these are using these latex. Okay. Now, in the international market, but what is happening is, sheet rubber is more produced in India, but in the international market, it is actually the technically specified rubber. What happens is they collect the latex in the cup, and the farmers, they will take it together and bulk it and make into a sheet. But in other countries, what they do is they add the acid into the cup itself, and it coagulates there, and take the coagulum to the factory and do it. But here, there is an advantage for the farmers is that, once you make the sheet, you can keep it with you, and you can sell it when the price is high. So once you coagulate in the cup, you lost it, and it is then the buyer's market. Now we have it is the seller's market, because it is we decide to sell, when to sell. That is the advantage with sheet rubber. And there is a lot of, another problem is that once you coagulate in the cup, you don't know the content of the rubber inside. It can be 35. It's a biological system. Therefore, it can be sometimes 35%. Sometimes you get 40%. So it is just like, the buyer comes, will say, oh, okay, it contains around 65% rubber, so we have to sell it for that. So that is the advantage. Okay. Now, this is the world consumption production data of natural rubber from 1900 to 2020. See, we started from very low to now it's around 14 million tons. And in 1961, the total global production was 3.9 million tons. In 2000, it's 7.5 million tons. And in 2019, it is 12 million tons. Now you look at the land area under cultivation from 8 million hectares to 14.41 million hectares is the increase. And this is the contributions from different countries, all East Asian countries, all Asian. This is a truly Asian product. Thailand has 4.9 million tons, Indonesia 3.1, Vietnam 1.22, China 0.774, India 0.697. Malaysia was the leader till 1985 to 90. And they became rich. When they became rich, what happened? There was no tappers. There was no tappers to extract the tree, harvest the latex. So that the same problem is facing Kerala. Kerala is one of the most the state with high standard of living. So we are going to face tappers problem. So we can think of robotics. Any startup group can think of doing that. It's a huge potential, not only in India. It is 14 million hectares under cultivation. It's a huge potential for it. If you visualize a robot tapping a tree, that will be fantastic. See, if you look at the NRSR consumption pattern, see from 1990 it is 5.1 million tons. See, look at, in 2000 it's 7.11 million tons, and 2019 it is 13.64 million tons. It's almost at par with production and consumption. Look at synthetics. It was 9.6, then it became 10. Now it is almost equivalent to that. This is the impact of radial tires. Radial tires consumes more natural rubber than synthetic rubber, and therefore this is that is why the gap between synthetic rubber and natural rubber reduced. And this is where it is used, actually. 65% of the natural rubber produced goes to tire making. 65%. And rest is, 8% for hoses and belts, 7% for automotive components, 5% for footwear, then 6% for medical gloves. That increased. Now it might be 8% after pandemic because a lot of people started making gloves. And then threads, foams, adhesives, and other latex foams and general rubber goods. See, my point is this. With all the advancement in polymer science, organic synthesis, still we have to depend on rubber treat for a natural rubber. There is an important, interesting scientific reason for that. That's what we are going to discuss. So this is the sum of natural rubber latex. It's a its particle size ranges from, this 0.1 to 2 micrometer. And if you concentrate, we will have the serum part because it will contain very low amount of rubber, which is small molecules that we call skim latex, and the other will be the concentrated latex. This is the pictorial description of rubber. Rubber hydrocarbon, then it is covered with phospholipid, which is covered with a protein layer, and which is charged negatively. But if you look at further to one single molecule, one end is protein, then 2 trans 1,4-polyisoprene, then isoprene unit 300 to 30,000, 300,000, 6,1,4-polyisoprene. At the end, we have a phospholipid and a magnesium. This is it. So trans omega terminal is a protein, then 2 trans, then all cis, then there is a di or mono phosphate, then there is either hydrogen bonding or magnesium in between, and there is a phospholipid. So it has got, so this is what the dry rubber structure of the rubber. So it will be branched because of these extra end groups. And if you look at the stress strain curve of this material, see the first one, HANR, that means high ammonia preserved natural rubber latex. We make a film and then we determine the stress strain curve, then it will be like this. This is the green strength, not the vulcanized rubber. It is green one without vulcanization. Okay, then if you look at the DPNR, if you remove the protein part, which is also attached, then if you use the DPNR, then further extracted with acetone to remove all the lipids, then still you have a very good strength. But if you remove the phosphate end group, it's gone. It's just like a synthetic isoprene. So this is so important in this green strength is very important in tire building because, tire is actually built before molding. Once we mix all the compound chemicals with this and then build over this, and then only we put in the mold. That building is very important, and for that the green strength is important. Therefore, then this will allow this high strength is because of the strain crystallizing nature of the rubber. That strain crystallizing is very important for glove manufacturing as well as in other functional requirements. See, look at that alternative sources of rubber also. Yeah, we can have alternative sources from Violi. US is spending so much money on Violi in there to make it is a shrub which is actually grown in a desert area. In our Rajasthan, we can try this actually. And dandelion is actually Kazakh dandelion. Earlier it was Russian dandelion. It is produced more in Kazakhstan. So they are not manufacturing, commercially producing, but you can have this natural rubber from Russian dandelion. It is grown in very cold area. We can try it even Kashmir. Then we have the heavier rubber, which is the one we are talking about. And IR, look at that. All natural rubbers have this phospholipid N group, and therefore we have that very good strength properties. But if you look at the heavy, IR, then we don't have. In fact, actually, this is that phospholipid N group that gives the nucleating agent for making a stress crystallization process, enhance the crystallization process, and give the very best. So if somebody can make that kind of a thing in an IR, then you can replace NR. But organic chemist has not able to make such a structure. So we think, this nature has created such a wonderful material, as if it was knowing that human Homo sapiens will be evolving and utilizing this wonderful material to its full potential. Isoprene. Yeah. Synthetic rubber is here. This is SR. SR is synthetic rubber, generic name. This is IR. Okay. Yeah. Okay. So this is the reason why we have still rubber plantations, or we depend rubber plantation for natural rubber. This is a simple reason. Okay, actually this was not knowing. So last 20 years work by Professor Tanaka from Kyoto University, who revealed actually this is the reason why we must be having natural rubber. And that is why IR is not performing like natural rubber. Yeah, but we were working with, from 1839, Goodyear discovered vulcanization, and Staudinger worked with this same molecule before he was, coining the word of macromolecule. Yeah. So in our institute, we are doing some work in this line. So the first and foremost thing is our, The first and foremost thing is our stakeholders, is our farmers. So therefore, we try to reduce their job. So we use some modification of the existing rubber sheet making machines, and a new sheet making processing machine is introduced, and many farmers are using this. Then we have good quality latex. See, sometimes for the price reasons, for labor reasons, farmers keep the latex preserved. And once you preserve, then it's difficult to make sheet out of that. So we have a method for making it and then keeping some of the important properties of the rubber. Then we have deproteinized natural rubber. See, in some of the engineering applications, this is important because protein absorbs water and it becomes hygroscopic and change the dimension, so that is not possible. So we developed a new method to make deproteinized latex directly from feed latex. Now it is being used commercially produced from centrifuge latex. So we created that with good properties. This is the process. And I told about the concentration of latex. This is a machine used for concentrating latex. It's actually using it is reversing the concentration and using the specific gravity of rubber, which is less than water. It comes to a top and we extract it out. So, but the problem is that the skim rubber, which contains around the byproduct, which contains only 5% rubber part, and it's difficult to coagulate. It's a laborious process. World over, it is like this. So we developed a new enzymatic method to quickly coagulate and recover the rubber. Another important one is that, we tried to, see, from 1991 onwards, Michelin had a famous patent, world patent, on solution SBR polybutadiene silica silane system, which is the tire used in all cars in US and Europe and all developed countries, because high-speed cars really need safety. So solution SBR is polybutadiene silica silane system is the one which is used in all cars in outside. There, we had a challenge, so we tried to address that through a epoxidation of the natural rubber. And we could make two patents, one with Apollo tires, combined with Apollo tires, but they are not making it. In our country, that need has not arisen, so still we are using natural rubber in our car tires. Another interesting point. So we thought of making some unsolved issues in rubber technology. This is one area we thought we must look into. We vulcanize rubber with sulfur, but we do vulcanize with peroxide also. But the problem with peroxide is that its scorch safety, which is the process safety, is very low. Process safety means, if you want to mold a compound, you have to keep it in the mold. Then at 160 or 170 or 150 degrees centigrade, then it should flow around the entire this thing before vulcanization starts. So this is an area where peroxide vulcanization lags from sulfur vulcanization. So we thought using these stable free radical to address this issue. The stable free radical, one is the 4-hydroxy tempo. The advantage with this that it won't react with an RO radical in presence of a C radical. So if there is a mix of RO radical and C radical, it attacks only the C radical. So that is what we wanted. So exactly we used that in our system, and we created that slope. It starts, that small area, which is very important for a processor. We use the same system, same stable free radical to devulcanize the rubber. So that is also important because huge piles of rubber is coming out, because we also produce large number of tires, and after 3 months use, every 3 months or 1 year, it will come back to the environment. And the government has come out with a new policy of it is the producer responsibility. Producer has to take it out and use it and responsibly dispose it. So we thought of making, so the existing process is the devulcanization percentage is 37.5. We use this stable free radical to get a 79% devulcanization. So this is the process. Actually what happens is, when you shear the rubber, vulcanized rubber, the sulfur bonds will break, but the sulfur bonds can rejoin. So we block that rejoining and increase the devulcanization process. So actually this idea we got from this idea we got from the free radical, controlled free radical vulcanization. So this idea came from that only. Okay, then, so this is the revulcanized properties. So there are few process now exists. One is dealing process and Levgum process, which is actually, they use some chemicals, but there is no need of using any chemical. Even without chemical, we get the same properties. But if you use our method, we can get a very good properties. So this is elongation, this is the tear strength. And another interesting one we are looking at is, when we look at the plastics, they have very high modulus. Then why don't we use that modulus to reinforce the rubber? Usually rubber, you find all tires black because we use nano black in reinforcing rubber. But it will have high specific gravity. So we used commodity plastic, we modified it, we controlled the process, and we used to produce a highly reinforced rubber which can float on water. That means it has a huge benefit for the producer, the manufacturer. For example, it is a volume cost that they calculate. So there is a 25% reduction in specific gravity means when you make 4 products, the 5th product will be free. So that's the point. But this is a very new idea, and I talked with Dr. Gupta of Reliance, so he is interested in this work. So we produced a road divider using colored road divider, and also we produced solid tires with a local MSME sector group. So this road divider probably this can withstand, so now our plastic road dividers will break easily, so this will last for 10 years. So probably we will be having it in CL. Okay, now another last point is this silica reinforcement. This is also very important because in tires, energy consumption is very important. So while running, it takes a lot of energy. So to reduce energy, the heating of the tire should be reduced. So that is provided by silica system. But silica has a problem with natural rubber. It has not an affinity. So this remains an unsolved issue. All properties except abrasion loss with carbon black is possible. So now we have developed some method to reduce that abrasion loss, and then it is, this is also a patent pending process. Okay, then I will, this is the one Flexil Benny was saying. This we developed, see, this is a sandwich of rubber and metal, and it has a particular strength and modulus, and we formulated it for the VSSC in 1993 or so, and still VSSC is using this formulation or its modified one. DRDO is using this formulation in their old missile programs. This is another. So this one is the one we made for Metro, Cochin Metro work. Then, yeah, we have all these testing facilities, and students who want to work with us in their project work can be sent to our institute for 3 months or like that. Then we have all these facilities. In addition to that, we have a new thing called incubation center for, if you have an idea on rubber product, we will help you to make it into reality. So this is the center, and we have made, these are some of the items we made recently. This is for the leprosy person, high voltage electrical mats. This is the waste from, there are a lot of nitrile glouses are used. We convert it into tiles because that glouse, we cannot burn it because it contains acrylonitrile. So we can't burn it, so we convert it into tiles, then adhesives. Then, of course, this is for the primary sector. So this one, slippers. This is I think 2 Bombay students did it. They want only natural rubber chappal, nothing else, and colored ones. So we made for them, and probably you will see in the market. Thank you.
Thank you, Benny, for a really wonderful tour de force on rubber. I learned a lot. I'm sure many of you did not know the structure of rubber had one ionic group in the end. That was a revelation, and certainly it's food for thought for many people to try and figure out how you can make it with other systems. So thank you very much, Benny. And
Yes, sir. So I would want you to stay back because we have to give away the memento. So yes, Professor George or Dr. George can come here. Yes, but probably he may not need it in Kottayam where he is. But you can go to Kashmir to do your experiments to do this. Thank you very much. So may I ask Professor Anil Kumar to please come on the stage? Yes. Thank you, sir. Thank you. And the memento also, sir. I would request Professor K. Shri Kumar to kindly come on the stage and receive this shawl and the memento from Professor S. Ramakrishnan. Yeah. And the memento, sir? Yes. Thank you very much. Thank you, sir. I have a few announcements before we break for lunch. Posters, students, please put up near the registration table. It is time for it. Certificates are ready. Please collect your certificate from the registration table. And now we break for lunch. And 2:30 we assemble back again to see all the posters. The book of abstract has been uploaded on the Symposium website. So these were a few announcements that I had to make. And please enjoy your lunch and kindly be back by 2:30. Thank you. Huh? Welcome back. We are now starting our session 10, which is oral presentation by dynamic student communities. And for this, we have as a chairperson none other than Dr. Chandana Basu, who was the founder of this department. So can I have Dr. Chandana Basu on stage? And to introduce Dr. Chandana Basu, I would request Dr. Vandana Jamdar to introduce her. Dr. Vandana.
Yes. Good afternoon, everyone. Dr. Chandana Basu completed her graduation from University of Burdwan, West Bengal, and secured her master's degree in physical chemistry from IIT Kharagpur in 1981. Later, she obtained her doctorate from IIT Bombay in 1988. She has gained her 12 years of enriching industrial experience from leading cable industry and non-tire rubber manufacturing sector. In 2003, Dr. Basu joined K.J. Somaiya College of Science and Commerce as assistant professor, and on completion of tenure, superannuated as an associate professor in October 2019. During this tenure of her service, she also has contributed to college administrative functions as member of the various committees like IQAC, examination cells, etc. Yes, as a researcher, she has completed 1 DST-sponsored and 3 Mumbai University-sponsored minor projects. She authored 7 research publications. Dr. Chandana Basu is one of the founder members and first course coordinator of MSc Polymer Science program. She has the passion to work for the betterment of the students. So, Dr. Basu, let me welcome you to chair this session. Thank you.
I would now request Dr. Vandana Jamdar to also present her a shawl and memento, which is a customary that we honor the chairperson by presenting the shawl and a memento. Thank you very much, Dr. Jamdar. And the memento, please. Thank you. And now I would request Dr. Chandana Basu to conduct this session. Thank you very much, ma'am. Please.
Good evening, everyone. May I request all the student participants who are going to present the paper in this session to come on the dais. Subhendu Shamanta from ISER Mohali, Nidhi Dilip Shirke, Rani Gupta, Aditya Birla Group, Mumbai, Ananna Rajamanur, and Sneha Sholi. Please come. First of all, I would like to tell all the presenters that your time limit is 10. When you will complete 8 minutes time, I will give you some hint. Please try to, because we all are running little behind the schedule, we would like to complete it on time. So please maintain the 10 minutes time limit. So first I invite Subhendu Shamanta, a PhD student from ISER Mohali, to start his presentation.
giving the presentation?
You take the mic.
So how can I change the slide? So, thank you everybody. So thank you Society of Polymer Science and Somaya Vidya Vihar to give me the opportunity to present my work. So today topic of my presentation is the folding of aromatic polyamides into a rare interchain beta sheet type of structure. So these are the my contents. So it includes introduction, design and synthesis, resultant discussion, summary and future scope. So charge transfer through bond is a very well-known phenomenon in the field of both chemistry as well as in the biology. But charge transfer through space is relatively less explored, but it hides the concept of or answer to the idea of very fundamental question in the field of biology as well as in the material chemistry. So among the examples of charge transfer through space, so in this example we can see the aromatic surfaces are coaxially pi-stacked with respect to each other, and these are separated by the rigid spacer. So as you're decreasing the number of spacer, the charge transfer through the space is getting increased. In another example, so this molecule, this is biconjugated molecule, when it's connected between the gold surface and between the STM tip, so this can act as a molecular wire and can have the conductivity. But very interesting is the next molecule, which among those two molecules, which do not have any covalent linkage, but because of the charge transfer through non-covalently stacked aromatically pi-pi coupled system, this can show the conductivity. Now you would replace the OCH3 group with the tertiary butyl group. Because of the steric endurance, it will not show any pi-pi stacking, there will be no conductivity. So now we can see the spacing of the pi surface and the distance between the pi surface is very important to show the charge transfer through space. Now if you want to find the example, the best example is the nature, because nature does the work that is very best, and that's where the concept of foldamers are generated. So in nature, the protein molecules which have a complex, which do complex biological biofunctions, they are mainly made up of tertiary and quaternary structure, and the tertiary and quaternary structure are mainly made up of alpha helix, beta sheet and gamma turn. Now artificial synthesis and characterization of alpha helix is relatively well established, but the same towards the beta sheet is relatively less explored. The reason is that you can synthesize the beta sheet strand, but because of the presence of the sticky end, it goes for the intermolecular aggregation, and that leads to insoluble aggregate formation. But to overcome this limitation, people have tried different strategies to synthesize the molecule. Among the best, one of the famous and recent one is the work of the Ivan Huk and co-workers, where they use pi-pi stacking instead of using the hydrogen bonding as a driving motivation to form the beta sheet kind of structure. And this beta sheet pi-pi interaction are strong enough to give the stability of this beta sheet structure, but they are weak enough to go for the intermolecular aggregation. Now we can see our target, the charge transfer through space, can be fulfilled if by means of the beta sheet kind of structure. So my target is to form the beta sheet kind of structure in the form of a polymer. Now next slide I will discuss my strategy. So we know that germaniolins, these oligoamides are very well known to form helical structure by means of combination of intermolecular hydrogen bonding as well as the pi stacking. Now what we do, we replace the 2,6-diamino-pyridine moiety with larger pi surface area. And not only this replaced with the pi surface area, but also we change the position of the amide linkage. And we had these three kind of model compound. And I wanted to see which among them had a better tendency to form the beta sheet structure. Now, it is very important to understand the formation of a beta sheet structure. So, suppose this molecule is in the helix conformation. In order to form a beta sheet structure, it has to rotate like this way. And if it had to rotate like this way, it will form this structure to have the beta sheet structure. But in order to doing that, you are actually losing the hydrogen bonding to have the beta sheet structure. Then the pi stacking interactions should be strong enough to give the stability of the beta sheet structure. Now, we did the computational study in collaboration with Dr. Dibendu Mollik. We saw that from naphthalene to pyridine, with increase in the pi surface area, the tendency towards beta sheet structure has increased. But even in the second molecule, it is in most population is in the helix conformation. But it is the third molecule where the amide linkage is 1,6, where the intermolecular hydrogen bonding and pi stacking both can possible. It shows a preferential tendency to form the beta sheet structure. That means not only pi stacking, but a collaborative effect of hydrogen bonding and pi stacking is important to give the stability of the beta sheet structure. So this is the synthetic scheme. I am not going to discuss in detail. I just can tell that when X is nitrogen, this polymer is P1, it can form intramolecular hydrogen bonding. When X is CH, this polymer is P2, it cannot form intermolecular hydrogen bonding. P1 peg and P2 peg are the post-polymers and modified product of their respective precursor polymers. This is the GBC and this is the model compounds. So in order to prove the intermolecular hydrogen bonding, we simply compare the proton number of P1 peg and P2 peg. So we can see, except the amide proton peak at 11 and that region, all other peaks for P1 peg and P2 peg are almost similar position. Only the amide peak of P1, where the P1, the amide proton is involved in intermolecular hydrogen bonding, that showed a distillate NMR peak with respect to P2 peg, where the amide protons do not involve in intermolecular hydrogen bonding. And this shift is constant even up to if you go for the 5-time dilution. And that indicates the presence of this proton NMR, sorry, not proton NMR, this intermolecular hydrogen bonding structure in this molecule, P1 peg. Now, to further understand the system, we did the Day2 exchange study, where we used the DMSO solution of both the polymers and added the D2O in 95:5 ratio and wanted to see the change in the amide proton peak with time. So in case of the P2 peg, where the amide protons do not involve in intermolecular hydrogen bonding, we saw very quick exchange of this amide proton with time. Within 15 minutes, the amide proton is gone. Similar study when we did for so there is this one is missing. So there is another, there should be another peak. So it's not coming actually. It's directly going to the next slide. Oh, this is missing actually. So here the NMR spectra was there. So for P1 peg, so this amide proton was the exchange of amide proton with deuterium was very slow, and it took more than 3 hours to totally exchange the amide proton. This spectra was there. So now is very important to discuss our experimental design. We have P1 peg and P2 peg. Now the basic difference between P1 peg and P2 peg is that P1 peg have intramolecular hydrogen bonding, P2 peg do not have any intramolecular hydrogen bonding. Now, so these structures are also not there. Okay, so we had our model compounds. The difference between the model compounds and the polymer is that model compounds do not have any this polymeric structure, it have only pyridine unit. Okay, so there may be a few possible outcomes. One is that P1 peg and P2 peg both can have folded structure. That time would indicate that in the presence of hydrogen bonding is not at all any directional to form the folded structure. P1 peg can only form the folded structure. P2 peg do not form. That time we can tell that the hydrogen bonding interaction, intermolecular hydrogen bonding interaction, is the main reason to form the folded structure. Now, before going for the folded study, so there is another structure is not there. There's something problem is happening. So there was the P1 peg structure was there actually. So it was better to show the audience to understand. Anyway, so the thing is that before going for this study, I do not have the spectras. No, ma'am. Actually, I do not have the spectras, so that is the reason. So when I tell. Okay.
The idea is that you have two different species, right? P1 and P2.
Yeah.
So how, continue.
Okay. So before going for the folding studies, it was very important for us to understand the concentration which we are working, the molecules should behave in a single molecular behavior, because multimolecular interaction can affect the folding. So that is the reason we did the DLS experiment, that was spectra was there. So there we saw below 25 micromolar concentration, the particle size was constant and it was very low. So that tells the single chain polymeric behavior at our working condition. Now when we compared anyway, so when we compared the UV visible spectra with respect to model compound and the polymer, so I do not have the model compound structure. So we saw with respect to model compound, where there was only one pyridine unit was there, we saw a 20 nanometer almost blue shifted absorption spectra with respect to polymer have the 20 nanometer blue shifted absorption spectra with respect to its model compound. This kind of structure generally happen in case of where there is H aggregated structure. Okay. This UV visible study we again did by means of computational UV visible spectra between the monomeric model compound and the trimeric compound, which had a beta sheet kind of structure. And there also we saw there is a 20 nanometer blue shifted spectra. Also this indicates the presence of this folded structure in case of the P1 peg. So if you go for the P2 peg, so it's not again visible there. So P2 peg what had, there was no change in the absorption spectra with respect to its model compound and the polymer. That tells or that excludes the possibility of presence of this H aggregated structure. If you go for the emission spectra comparison between the, this is the model compound, this is the polymer. So if you compare the polymer and model compound, you can see this in polymer is the Cohen's emission spectra with respect to model compound, and if you normalize this spectra, you can see at 505 nanometer there is an increase in the intensity of the excimer peak. That tells the presence of this cofacially pi stack structure in case of the P1 peg. If you go for the P2 peg, so it's not again coming. So it in case of the P2 peg, so what happened? There is no change. Both the cases, model compound and polymer has the same emission spectra. That tells, or that it tells the there is no folded structure present in case of the P2 peg. That means hydrogen bonded interaction as a pipe and pipe-stick interaction is very important to have the molecule as a folded structure. Now with increasing the temperature, P1 peg, the emission intensity is increasing, and at 100 degrees centigrade temperature, this molecule almost attended goes to the level of a monomer. That, and also if you go for the normalized spectra, with increasing the temperature, you see there is a decrease in the emission excimer peak with increasing the temperature. That tells that this molecule with increasing temperature goes from a folded to unfolded conformation. Now similarly, when we did for the P2 peg, which already in unfolded conformation, there was no change in the spectra as well as absorption as well as the emission. Now, the thing is that, so we saw there the P1 peg with respect to model compound had a much folded, better folded structure. But the thing is that there you saw the increase in the excimer peak, but the excimer peak was not very intense. There may be few possibilities to not to have the intense emission spectra. Maybe the one possibility is the presence of the rigid spacer between the pyridine unit that do not allow the pyridine molecule to come closer to each other. Another is that the H aggregate which is forming there, that is dynamic. So whatever be the reason, to overcome this our limitation, what we did, we incorporate a gas molecule which had a pi surface area, and this will incorporate within the pyridine molecule, and that will give a kind of host guest or the guest reinforced secondary structure, and this is a kind of cofacially pi stack beta sheet kind of structure can form. And this was monitored by means of UV visible as well as then this emission spectra. So this is also not there. So if you saw the UV visual spectra, show there with increasing the guest molecule, this UV visual spectra shows as a 373 to 333 nanometer blue shifted absorption spectra happened. And also if you go for the emission spectra, there is a Cohen's emission as well as the increase in the 505 nanometer excipic peak formation. That tells the possibility of the presence of the cofacially pi stack beta sheet kind of structure. Now if you go for the similar study with the P2 peg initially do not have any folded structure, but when you incorporate the gas molecule, it also showed the gas molecule reinforced secondary structure or this cofacially pi stack beta sheet kind of structure, and that also we monitored by the presence of the blue sheet absorption, Cohen's emission as well as the increase in the excimer peak, exciplex peak formation. Okay, now with increasing the temperature, we saw that for in absence of any guest molecule, P1 peg, increase in the temperature went from the folded to unfolded conformation. Now here in presence of the guest molecule, its complex is very stable. with increasing the temperature, there is very little change in the absorption as well as emission spectra can be observed. Now the similar thing if you go for the P2 peg, yeah, so there is no change up to 100 degrees centigrade in case of this host-guest complex. The similar study if you go for the P2 peg, which do not have an intermolecular hydrogen bonding, where the beta C structure was only by pi stacking, there you saw that with increasing temperature, this molecule going for the uncomplex to complex to uncomplex state. Now, this is the thing. You can see the rate shifted absorption spectra as well as increase the emission spectra. Okay, that tells the complex to uncomplex state transition. As a summary, I can tell that P1 peg and P2 peg, the difference where the P1 peg which had intermolecular hydrogen bonding, this instantly fold up kind of folded conformation, whereas the P2 peg which do not have an intermolecular hydrogen bonding, that was in a random coil structure. But in presence of the gas molecule, it was reinforced to a cofacially pi stack beta C kind of structure, but which was thermally unstable. But in case of the P1 peg, in presence of the gas molecule, this was thermally stable and not at all disturbed by the temperature. So I think I have exceeded the time. So just 1 minute. So future scope, I am not going to details. So I'm just, as a gist, I am telling that our main goal was to have the conductivity through space. So what we did, we checked this molecule, the folded molecule conductivity as such. So with collaboration with Dr. Sabyasachi Mukhopadhyay, we did check the conductivity. Where we saw the P2 peg molecule which do not have any folded structure that had less conductivity with respect to the P1 peg in absence of any gas molecule itself. So that showed in the red color, increase in the conductivity. But in presence of the gas molecule, the further reinforced structure showed almost 10 to the power 2 times increment in the conductivity. That tells about this molecule can be acted as a kind of conducting material, but we need to optimize our this morphology better and better. And another study, another experiment is that, so I'm telling you, so in the poster also somebody also asked me that you tried with the naphthalene, why don't you try it with the different pi surface area? What is the anthracene, pyrene? So we tried with the different pi surface area. So there you saw that this molecule has a very specific selectivity in presence of the guest molecule. So we used some indirect study to observe the selectivity. We added the anthracene molecule. So we had the two possibilities. It can stay as an outsider or can go inside the pocket and kick out the naphthalene molecule. At that condition, we shine light here. We do not show any anthracene dimerization. Now, similarly, at this condition, if you add a better pi surface area molecule, pyrene here, so pyrene goes inside and kicking out the anthracene. And if you shine light at this condition, you can see the anthracene dimerization here. So if you go for the selectivity study, it's pyrene greater than anthracene greater than naphthalene. That means better the pi surface area, more the selectivity. So as a acknowledgement, I just wanted to thank my supervisor, Dr. Rajkumar Roy. I wanted to thank Dr. Dibyendu Mollik for doing this computational study, Sabyasachi Mukhopadhyay for doing the conductivity measurements, also Isaac Molly Center Facility, Departmental Facility, and also again I will thank Society of Polymer Science and Swami Vidyavihar University to giving me this opportunity to present my this work, and also my family member are present. And also this paper has today come online and it is published to Polymer Chemistry and also selected for cover page. Thank you.
Thank you, Shubhendu, for the nice presentation, though there was some technical problem, but you could manage it very well. Thank you. Please be seated. Okay, 1 or 2 questions.
Exactly, sir. Kind of polymeristic structure, generally this kind of thing happen. Exactly, sir. Specifically, not.
Beta, of course, you show me a structure there. Any that structure you have. Any structure, you can just show me any structure. You take your slides back.
No, it's not going actually.
No, for example, you have just shown arrows like this, that beta arrows, no? Arrows.
Okay.
And on the one other side of it, you had something like this, some what is it, coil or something.
Helical
like
structure.
So what is that called? What is that structure called?
Helical structure, that is. So
what is that helix?
Actually, so Jamedi Lane and his student Evan Yuk. So these are the peoples, they generally, this is the oligoamides, they generally prepare. It's very famous. So
you mentioned about folding. Somewhere you mentioned about folding, no?
Yes.
Folding. Is there any, what is that, folding which is happening in the nature?
Yeah, so polymers, all the things are in the nature, na?
Tell me, what is protein folding?
Protein folding is the, sir, in presence of, so protein, so there is in different structures. So alpha helix, beta sheet, gamma turn. So by means of these things,
So you mentioned gamma, beta turns and gamma turns.
beta sheet and gamma turns.
Okay, so that's protein structure.
Yeah, mainly the protein structure.
So that is the answer.
Yeah, okay. Okay.
When I asked about nature, so in nature this is.
Okay.
Have you heard of an Indian scientist? You are a PhD student. You are talking about beta turn, all these things.
I think you're talking about Ramachandran.
Oh, okay. You got it maybe even before I asked. Thank you very much. Ian Ramachandran.
Yeah, okay. Yeah.
So what is his contribution?
I think this is Ramachandran plot. So, so exact plot, frankly,
You have heard of
yeah, obviously.
Thank you. Thank you, Shubhendu.
Yes, thank you.
May I now invite Nidhi Dilip Shirke, a MSc student from Somaya Vidyavihar, to do the next presentation.
Good afternoon, everyone. Myself, Nidhi Dilip Shirke. I'm from MSc Part 2 student of SK Somaya College. Today, I'm going to present on environment-friendly lithium-ion battery separator, a comparative study. The purpose of doing this to reduce dependency of the fossil fuels and for the biodegradable property and the renewable sources. So, introduction. The lithium-ion batteries we see in the various like in various things like in the mobile phones, the automobiles, in the digital camera, in the computers and the other fields as a high power density and the superior electronic properties. Then the problem of we face in the lithium ion batteries, they are mainly prepared from the polyolefins and it is a petroleum base. So, lithium ion batteries is a porous membrane that facilitates the transfers of the ion between the anode and the cathode to prevent to electric circuit. So, conventionally it is in the market available polyolefin based petroleum based lithium ion battery separator. So, there is a strong need or it is a demand for the lithium ion battery separator. So, it is environmental friendly material for a sustainable society. So, the new research frontier have given the ideas to change the polyolefins through two other alternatives like they are biodegradable like first is the cellulose base and the other one is the chitin base. The chitin is a very sustainable battery separator. So, these are the two alternatives and it is easy to engineer the various properties we see in the polyolefin based lithium ion battery separator. Like we can achieve various properties like pore size, diameter, thickness, wettability and other the mechanical and the thermal properties. So, the comparative study of the property functional attributes the biopolymer based separator. Then the next attributes, the separator membrane must be fulfill the following properties like the chemical and the electrochemical stability and the other thickness approx the 25 micron, the porosity more than 40%. The other various properties like pore site, it should be follow a path or a total structure. The other permeability, it should be a uniform permeable. Then the other is the mechanical strength should be reduced in 1000 kg per centimeter square. Then the other physical properties like wettability should be wet and retain electrolyte permeability. The other one is the dimensional stability should be over wide range of the temperature. So, for the thermal shrinkage like then the less than 5% to 60 minute after 60 minutes at 90 degrees Celsius. So, the various problems we see like in the lithium ion batteries, they shut down quickly for in case of any runaway reaction. So, exchange of the lithium ion battery to polyolefins to a cellulose base, there is a cost reduced by economically like 20%. Then the next is the cellulose based lithium ion battery separator. We can there are 4 methods for the fabrication. Then the first is the solvent casting, also known as evaporation method. In
that fabrication method, we do cellulose, we dissolve in the solvent. So we do a flame and then the solvent is evaporated and it's this precipitate, it's a membrane. So other one is the doctor blade coating process. It's also another method of fabrication. So also it's a when the solution is prepared, then it's poured into a plate and the blade is known as the doctor blade coating, and the coating while it is spread, so the solvent is evaporated and the removal part is the material. So the other one is the non-solvent base, is also known as a phase inversion. It is a two-phase inversion process. Like first is the we can do a solution and do like a polymer plus solvent, and the other one is the last one is the electrospinning process. Like the electrospinning process, the electrical gun, or it is a syringe, like its syringe is a negatively charged and through where the membrane is the positively charged. So when it is poured, so the solvent is evaporated and the precipitation is the form. That thing is the membrane. So the next is the cellulose based battery separators. Like it has a better future due to its low cost and the hydrophilicity, high dimensional separatity and the other mechanical properties, and it also in good in the solvent uptake. Like fabrication is still a challenge. If the fabrication methods that we are discussed previous slide, that will be good, so it will be get a better result. So the polymer based on the natural resources present like platform material for a sustainable energy. Then the nanocell shows promises, and the mesoporous separator can be fabricated through the cellulose based separator. Then the it's a cellulose based composite battery separator, like cellulose and its derivative provides a multifunctional platform in lithium ion battery separator. It's having the high various property as we seen in the polyolefin base, like other properties, good film performance property, high porosity, hydrophilicity, and it's also excellent stability. It's a cellulose based battery has a huge development and potential to a better future in the market. Then the next is the lithium ion batteries is made up of cellulose, and we can also use the other derivatives of the cellulose to wrinkle sealage and recrystallization, which gradually affect the lithium ion efficiency. The various preparation methods are like the process of mixing, coating and the cutting cellulose base through a lithium ion batteries coating. Then the other derivative of the polyolefin, the first is the cellulose and second is the chitin base. The chitin is the most second abundant biopolymer through cellulose. It's a non-valent fiber. It exhibits electrolyte uptake capability and migrates various performance like it's the cellulose base. Another, this is through centrifugal jet spinning technique. There is a way to get hierarchically aligned like self-assembling chitin nanofiber. The chitin membrane through like centrifugal jet spinning, so we get. Then the other is the why chitin is a best material for the separators. Like in the lithium ion batteries, they have high energy capacity like 35,000 weight per kg. Critically drawback is to uncontrolled growth of the lithium derides, which limits the life cycle of the lithium metal battery. Also the safety issue due to its internal short circuit. These protruding lithium ion batteries arises from a homogeneous distribution. By introducing various regular nanopore array or by creating micro pattern on the lithium anode. The chitin fiber prepared by a centrifugal jet spinning method and it work as a non-bowing met dentin. Chitin has a large affinity due to its unique coordination with functional group. Chitin has its amide group, so it's a positive for this purpose. Then the next is the conclusion. For renewable battery separators could be based as a cellulose and other biodegradable polysaccharides like sodium alginate and chitin. There are also cellulose to a certain extent, as they also develop excellent electrolyte uptake capacity, high thermal and chemical stability. The use of the renewable polymer will transit toward a more sustainable society based on the circular economy. So materials should be maintained as long as possible. So the main purpose of doing this is the better future and a green future for the separator. Thank you. Thank you.
The session is open now. Please ask question.
Okay. Cellulose, from cellulose. It's a cellulose derivative.
What is the source? Where is it coming from?
From environment. It's the second most abundant nature.
But what is the, so where is the, it's a natural thing. You
Yes.
said it correctly. It is a second abundant, that also is, you are correct. But where is the source? Where is it coming from?
Yes.
Any guess?
Cellulose.
You said it
and,
is from nature.
Nature, yes.
Is it vegetarian or non?
Yes, non-vegetarian.
Are you?
Shell, from shell.
It is from the sea.
Sea, shell.
Not shells. It is, so, it is not vegetarian.
In solvent, in xanthine, and the other solvent is MNO. N-methyl morphine. MNO. MO.
Why is it that cellulose is totally solid?
Actually, due to its hydrogen bonding, it is not soluble in many solvents. So it is like xanthine and the MNO is so it is soluble in the both solvents. Okay.
Very widely used method, okay? It's a derivative of cellulose. What is a cellulose derivative? Which is easily soluble. Because
By pouring and evaporating.
No. You said hydrogen bonding is what makes it
Yes.
insoluble. So I have to do something to remove the hydrogen bonding. So what will I do?
Break the hydrogen bond.
So I have to. I should not have OH group, right? So what should I have? I replace the OH with something else.
Okay.
What will I replace with?
OME.
So can I replace it with some other? You know,
Okay.
like he said, I can replace it with ether groups. I
Yes.
can replace it with acetate groups.
Methyl group.
Okay. Okay. I can convert it into, like he said, cellulose ethers. Okay, or cellulose acetates, and they're soluble.
Yes.
Okay, so I make a film out of that. And why can't I use that material?
So that is the method.
Yes.
The method to avoid hydrogen bond.
And because you don't have a hydrogen bond, now it's readily soluble.
Soluble.
Okay? So cellulose acetate is readily soluble, cellulose ethers are highly soluble. So I can make a film.
Yes.
Okay, and why can't I use that? Can I use that? You think
Yes.
you can?
Yes, sir. We can use that.
You should think of using that, okay? Because you can make cellulose acetate films. Very well-known films are available.
Yes.
But then you have to create some porosity in them.
Yes, sir.
Okay, which you can do. Okay. So
Okay, sir.
I have a question. So my understanding is that ketene to chitosan and then biopolymers, something like this, some process is there. So ketene alone, we have to go for biopolymers, correct?
Yes.
From ketene to chitosan?
Yes.
Is my understanding correct?
Chitin, only chitin.
Chitin, well,
Chitin.
I have no authority to say, but I think, you know, Professor Pillai, it is go to from ketene to chitosan? Yeah.
It's possible. Conversion factor.
Yes.
Very good question.
Thank you, sir.
Thank you, Nidhi. Excellent presentation. And I am very happy that you have maintained that 10 minutes time. Okay. May I request now Rani Gupta, she is from industry, Aditya Birla Group, to present her.
Hello. Hello everyone, good afternoon. This is Rani Gupta from Aditya Villa. First of all, many happy returns of the day to you, sir. Because of only you, we got this opportunity to speak. And thank you everyone for giving me this opportunity to speak in front of you, to have an oral presentation. So, I am from Aditya Villa. My topic is toughened epoxy system for composite pressure vessel. As I am talking about the cylinder, as we all are in chemical industry, so let's start this presentation with one small safety share on cylinders. As we know, day by day there is an increase of the accident happen due to the cylinders. So just a small precaution, we should make sure that while leaving the house, just make sure all the knobs is closed to avoid the accident, to avoid the gas leakage. Make sure all this is closed. Whenever the distributor is providing the cylinder to your house, just take the help of them to fit it properly, because he is only the correct person to fit it other than us. So make sure we will take the help of that guy to fit that. So these are the small safety norms we should follow while using the cylinders. So yeah, so only I have 8 minutes time, so I just want to cover my topic. So my topic is toughened epoxy system for composite pressure vessel. This is the type 4 cylinder which completely replaces a steel cylinder. Next one. Yeah, this is the type of cylinder. Type 1, that is the fully metal that we are currently using. Type 2, that is a hoop wrap aluminum, which is full of aluminum but wrapped with composite. Type 3 is the fully wrapped carbon composite, but the liner is of aluminum. And the type 4 that we are talking today is fully of polymeric material. You see, this is just a small prototype of the cylinder. This one, maybe the end of this year, this type of cylinder will be in our house. So this is fully a polymeric cylinder. How type 4 cylinders added value? It is because it has the translucent body. So we can easily check the level of gas. So when there is then we will easily to identify when the time of refilling will come. So this is what there is the translucent body to check the LPG level. This is how you can see. Here is the gap, this one. So you can easily check the levels of the gas. So you should know when the time come to refill. Otherwise हम लोग अभी ऐसे gas एकदम बंद हो जाता है. So it is quite difficult nowadays. It is resistance to corrosion. It has good impact and environmental condition. It is called as a 3-layered cylinder because the first layer is of the HDP, which is made by the blow molded one. Another one is the liner of the composite layer, which is provided by us. And the third one is the HDP liner, that is the HDP jacket. HDP liner, that's why it is called as a 3-layered cylinders. It is totally lightweight, it is 50% lightweight than our current steel cylinders. It doesn't have the, even it is good corrosion resistance to it, don't have the chance to have the stain and marks on the surface. And it is very aesthetically appealing as you see, as it is of the polymer. Another one is how this idea came in our mind to go for the toughened system for this cylinder. Previously, we are using the conventional epoxy system. So what we observe is, by using the conventional epoxy system, as you know, the epoxy has the chances of brittleness. So brittleness leads to the cracking, and the cracking leads to the permeation of gas, which is not at all acceptable while we are using the cylinder for the gas, because gas leakage is the most important property while we are providing the system for cylinders. So yes, the conventional epoxy system providing the permeation. So the thought process come, why don't we replace this conventional epoxy with the toughened system? So yes, We process the toughened epoxy. This you can see, this is the common cylinder, that is the explosion rigs, you know everyone. There we can't check the level of gas. It is heavyweight, it is corrosion, it remains a stain, it is not much appealing, it is easy to damage, it is easy to burst even, and the transportation is also quite risky. As you see, they are loading is like this, so there is a chance of accident is more in these cases. But if you go for the toughened epoxy system, it is obviously it is 50% less weight. So the transportation become easy, its appealing is good, it is non-corrosion, so it does look good. Only the need we have to take, like, you know, abhi hum log cylinder pe directly we keep the heated material, so you have to just take care that it is of HDP, so we can't keep the heated material on the cylinder. It is durable and it is the latest technology in the market. And we, the Aditya Birla toughen system, is only the one in whole India as well as the global providing the epoxy system for this type of cylinders. These are the processing properties that we have to maintain. The toughen system that we are providing have the, we can say, the slow reactivity as well as the processing. So what happened, due to which it got the long working life. Because of long working life, the impregnation of the glass fiber with the epoxy got the time and it became the easy of processability. So because of which the mixing ratio of the resins and hardener that we use is by 100:98. The mixed viscosity, the epoxy and the curing system that we are using have very less viscous. So as I said, it ease of process for the glass fiber for impregnation. So it is only 600 to 900 millipascal. Then the gel time at different is 80 degree, 100 and 120. That is what we can say. If you process that cylinder at 80 degree, you get 45 to 55 minutes, and same for the others like 100 degree, 120 degree. And the TG that we achieve is around 130, it's 110 to 130, it's at the good heat glass transition temperature. And the flexural strength is 100 to 115, which is the most needed for while filling the gas into the HDP liner. The flexural strength is most important because the expansion is the test that is processed while making this cylinder. Advanced material newly developed toughen system show the higher fracture toughness and the strength than the conventional epoxy system, which you can easily see. The conventional, that is critical stress intensity factor, that is fracture strength and the energy release rate, you can see the difference. The Aditya Birla toughen system had the higher toughness as well as the fracture strength as well because of this toughen system. Yes, as I already discussed, the toughen system, it has a low processing viscosity, provide a long working time at ambient temperature, which improves the fiber impregnation. Then it has a good, it's fully covered, cured component prepared from the exhibit excellent surface, mechanical and thermal property, which is the most needed for the gases, LPG gases. This system not only used for the LPG, but is also used for the CNG gases as well. Only the difference is of the fiber. For the LPG gas, we are using the glass fiber, but for CNG, which required the high processing than the LPG gas, it can be used by the carbon fiber. For CNG, we are processing it with the carbon fiber. Yes, and we are, as I told, we are only the one manufacturer all over the India as well as the globe for providing the toughen system. So yes, it will be soon in your home. This is just a flow diagram to easy to understand how the process works. Here is the parison of HDP, which is blow molded. Then it processed for the nozzle. There is one question by the Ramakrishnan sir. I will answer it right now. Yes, so the parison of HDP, then it goes for processing. It's a full robotic technology. With suppliers in India, you know very well. Supreme is only the one supplier and the Technoplast in India who is making this cylinder using our toughen system. So yes, it is fully the robotic one. Here we see how the robots take the Parison from the blow molded parison from the machines, and then it processed for the filament binding. It is not, it is something blur. It is a filament binding process where the fibers goes into the bath of resin and hardener, and then it wrap into this parison. So it takes 61 cycles of the wrapping happens on the HDP liner to make it reinforced. Because you know that today the polymer is fully replacing the steel by using this glass fiber only. So it is making it reinforced. Then this type of, after reinforcing, this type of cylinder we can easily see. Here it's made. Then there is a nozzle fitting, happens with heat sealing method at 12 Newton per minute. After that there is a winding of fibers also happens here at the nozzle as well to make it again more protective or reinforced. After that, this what I am talking about. This is this HDPE liner. You can easily see this one, and you can easily open. This is the injection molded one. Then this epoxy toughened system, this parison of HDP, the first one, this one goes into inside this, then the whole cylinder look like this. Then you can easily see the gas level into this through this gap. So this is how the cylinder looks at the end. And here, this one. So yes. For detailed information and for more system of epoxy, you can easily go on this website and have multiple systems. You can explore for different application as well. This is from my side. Thank you.
Thank you. Thank you, Rani.
Yes, ma'am.
Please, questions, please.
Yes, sir.
What is the work you are doing in epoxy?
Means? Yes, sir.
In the laboratory work you are doing in epoxy, with epoxy.
Yes, sir. I am working in different epoxy applications.
So, just
this for this toughened system?
anything. For
Okay. For this,
yeah.
we are making that formulation for making that, that I told about this bath of epoxies, resins and hardener bath. We are making the resin and hardener for this, in which the gas will feel, the gas that we are working. I am working, you can say.
Okay. You skipped a comment on the cost. I mean, so it's for middle class, lower middle class.
The cost is same
no,
as...
you said costly.
Yes, sir.
Costly. You mentioned in the slide it is costly.
Costly in the sense is like only the deposit. The deposit we need to pay to the gas distributor is higher as compared to the lower. Right now we are paying only 800, 1,000 rupees. Maybe there is a case for this, the deposit will be around 3,000, 4,000. So, but it is only the one time, as my first slide please. As I say, life is more valuable than money. So it is only the, I know, I can talk about, because it is only the one-time cost, 3,000, 4,000. It's only the, and it is the deposit. Yes, sir? Sir, because the processability is expensive as compared to the steel one.
May I?
Yes, sir? Sir, by heat sealing method.
Regulator.
Sir, ये था.
After on.
Sir, yes, sir. Yes, sir, same nozzle. It is by during processing only we are making the hole. Then again there is a one system. Then we directly feed that nozzle, and then we heat seal it. Then again we provide the wrap. Yes, sir. It is the metal nozzle.
Is there any study regarding stacking of the cylinders one on
yes,
another?
Yes, as I told, the unit only unit to protection while transportation. We can stack like this cylinder.
Generally, all the cylinders are vertically stacked
See,
and
next
horizontally
one.
also stacked. You have showed in one of the.
This one,
yes,
right?
Yes.
If you see, currently this type of stacking happens.
Yes.
But while we are using the HDP, we can't stack like this. It should be in one line. You're not overloaded and everything.
Yes.
Just this.
So this can increase the
Yes, sir.
logistic cost, na?
They will take care, na sir, because it is, we have to pay 3,000 as a deposit, so even the distributor will take care. Arey baba, apna salary se katega. So he will take care of it.
Approval has already come for the Indian Oil Corporation.
Yes, sir.
The approval has come, so I think it is within the
It
next.
is already 3,000 per day manufacturing is already
They
going on.
started. There are companies have already started. I think
Yes.
in the next 1 year you will all see this in the house.
Yes, sir.
What about its gas permeability rate?
Sir, as per the gas, gas permission, it should be less than 10.
That is the specification. What is your value for your cylinder?
Sir, it is 0 now. Because when we are into
Zero.
conventional, it should be less than 10. So we are around 9.5. Now it is 10 by the toughen system. But when we are using the conventional one, it is more than 10. It is 30 gram this type of. So it is not acceptable. That's why we switched to toughen system for that. That's why we are currently they are using the toughen system because it has good
But
permission.
still you are not told the value. For your toughen system, what is the permeability rate
Permeability?
of gas through this cylinder or through this polypropylene?
Sir, I didn't get the point actually.
He's asking.
Gas diffusion or gas permeability?
Permeability.
That's important, no? If gas is leaking through the cylinder,
So this happens while we are using the conventional system, there is a permeation loss, the gas leakage is happening. That's why it got... Yeah, it is 0 actually. Permeation loss is 0 because
I don't think so. Cannot
because
be
we
zero.
individually visited and saw that Supreme, all the list. They have mentioned everywhere it is 0. Permeation loss is 0. Maybe it is less than 10 because their requirement is it should be less than 10.
Okay, you look into it.
Sir, I will definitely check and let you know. Yes, sir. It is from Reliance.
I just want to know.
Yes, sir. So we are not making the HDP liner. Sir, the grade we are using, that is the second grade. It is 2. Yes, sir. So you are from Reliance, you know very well what you are supplying to Supreme, you know very well than me, sir. I am the, Yes, sir, he is from Reliance, so he know. Yeah. The grade. Sir, actually, I am more into the toughen system. I know he is from Reliance. I spoke Reliance.
No.
Yes, sir.
No, you
We
should
are
know
using
it.
the HDP grade of 2. Yeah. We'll talk to you later. Yes. Yes, sir. Thank you, sir.
Thank you, Rani.
Yeah.
May I request now Ananya Rajanur, MSc student from Somaya Vidya University, to present.
Hello? Hello? Can everyone hear me? Good afternoon, everyone. And I'm Ananya Rajamanur, a second year student from Department of Polymer Science, SK Somaya College. And today I am going to present a short PPT on the amelioration of polypropylene hernia mesh material. So first we'll start with the introduction. So basically what is a hernia? Hernia is a bulge in the visceral contents across the abdominal wall. So basically now we are seeing in the world one of the biggest conditions is hernia, and we treat it through surgical meshes, and one of the most common materials used to make surgical meshes is polypropylene. It is used in the form of used as surgical meshes in the form of sheets inserted in an organ. However, polypropylene suffers from a share of problems such as high chance of infection due to action of microorganisms. So now we'll talk about how exactly we can improve polypropylene meshes. Polypropylene meshes are susceptible to microorganisms which may cause serious complications and may also prove fatal. To solve this problem, surgical meshes showing antimicrobial activity should be prepared. One of the ways to achieve antimicrobial activity is to increase in hydrophobicity of polypropylene meshes. So, the more the material is hydrophobic, the less is the antimicrobial activity. This is because the hydrophobicity of the polymers enhances their binding to lipid bilayers and induces collapse of the polymer chain in the solution, reducing the affinity of the polymers for the membranes. And what we are going to do is we are going to take PMMA coating and apply it on the polymers as on the meshes. So, we will talk about the materials and the methods. So, basically first we synthesize the PMMA coating, which is antimicrobial in nature. Then we take samples of polypropylene meshes, that is proline meshes, and categorize them as coated and control. The control will be the mesh which is uncoated. PMMA antimicrobial coating will be applied on the polypropylene meshes, and we shall consider either dip coating or spray coating method for coating of medical devices. After coating, the meshes shall be dried, and then we characterize the mesh samples for its antimicrobial activity. So, future work, which is the preparation of antimicrobial hydrophobic coating of polymethyl methacrylate polymer, application of antimicrobial coating to the mesh, evaluation of the antimicrobial activity of the mesh, assessment and drawing conclusions from results obtained by comparing the activity of the coated mesh with the uncoated mesh. I would like to express special thanks to my professors, Dr. Dali Davis and Dr. Padma Vankar, for the guidance and support in this presentation. I would also like to extend my gratitude to the Institute of Somaiya Vidya Vihar for giving me the platform to present today. Thank you.
Question answered, please.
So, we are not done it yet. We still, yes, sir. My biggest literature source is PUB Med. So, what I have done is I have analyzed I have written a report of all the cases in which the mesh failure has happened due to the infection of the at the site. So, when we put the mesh at the site of the injury, so we have observed that there is a lot of microorganisms which come in contact with it, which cause infection.
Why are you, there is a Garda chemicals?
That is over here.
Okay. So you did not do the work anywhere?
No, not yet, sir. We're still doing it.
So you surveyed the literature?
Yes, sir.
You made use of PubMed source?
Yes, sir, PubMed.
What is PubMed source?
Sir, it's a like all the medical cases are given in a format like the background and the abstract and the results. So all of them are given in that.
Any other question? Thank you, Ananya.
Thank you.
Very nice presentation. May I request now Sneha Sholi from Maharaja Shivaji Rao University of Baroda. She is a PhD scholar.
Good evening to one and all present here. My name is Sneha Soli Abraham, and I am doing my PhD under Professor C.N. Murthy from the Maharaja Shivaji Rao University of Baroda. Today, I will be speaking on light-induced atom transfer radical polymerization using copper nanoparticles. So just to give a briefing about the atom transfer radical polymerization, which is also called as ATRP, it is one of the technique of control radical polymerization which was reported in 1995. So as we know that long back, the Karash edition in which in the presence of the peroxide, the CH bond gets activated and it gets attached on the alkene. So similarly, they studied about that what happens in the presence of the metal catalyst. So they saw that the CH bond does not get activated, but the CCl bond gets activated and gets added onto the alkene. This mechanism, which is called as the atom transfer radical addition, which is also called as ATRA. So ATRP is mechanistically similar to that of ATRA. It's just that there is more than one addition step. So here the main components of ATRP is that, so firstly it is the alkyl halide, which is the initiator which is used in ATRP. And then there is a metal catalyst which can mediate in two oxidation state. And this metal catalyst, which is in the +1 state, it is called as an activator. It will abstract the halogen, it goes to the +2 state, and this alkyl halide will initiate the reaction. Now if we add the monomer further, it will add on to the monomer and then the propagation step take place. This metal catalyst, which had gone to the +2 state, then it gives the halogen back, and then the dormant species is being obtained and the metal comes back to the +1 state. This is the mechanism of atom transfer radical polymerization. So the main thing in ATRP is that to maintain this equilibrium. So the thing is that the deactivation should take place more as compared to that the activation. Because more the deactivation, more will be the formation of the dormant species, which will result in the less formation of the radical, the active radical in the system. And due to that, the termination process will take place like in a less manner. And so ATRP is a very good technique to control the polymerization and to get a good PDI polymer. So because of this ATRP technique, and it can be controlled in a very good manner, so the predetermined, like what we want, the predetermined molecular weight and of different composition, topology and functionality, all types of polymers can be obtained via ATRP, and it can be used in a huge number of applications. Oops, sorry. Like I have. Okay. So there were little bit drawbacks of ATRP, that the metal catalyst loading was large. There was undesired accumulation of copper-2 species because the copper-1 gets oxidized to copper-2. And there was little bit difficulty in controlling the equilibrium, that is the activation-deactivation step. So there was a report from Yaxi sir that he's a pioneer in this CRP technique, and he reported that why not using the copper, instead of copper-1, which is the activator, why not to use copper-2 species? But to activate the ATRP mechanism, the copper-1 is very much necessary. So he produced zinc oxide semiconducting nanoparticles, which in the presence of the UV light, it gets activated. The electrons from the conduction band, it went to the copper-2, it reduced the copper-2, and it gave copper-1 species, which will then initiate the polymerization reaction as mentioned earlier. So keeping this in mind, we thought like similar work can be done by us also, and by like the previous idea. So we have one of our colleague in the same university who is working in the nanoparticles. So she prepared the cuprous oxide nanoparticles, which she used in the CH bond oxidation in mild conditions. So our aim was to do the polymerization reaction in milder conditions. So we thought, why not to use these cuprous oxide nanoparticles in our polymerization reaction? And luckily, we got the result. So here I have taken the methyl methacrylate, did the polymerization in the presence of the ethyl alpha bromo isobutyrate, which is the initiator. And when the visible light, in the presence of visible light and the cuprous oxide nanoparticles, it gets activated. The electrons from the conduction band, it reduces the copper-2 bromide into copper-1, and the polymerization will initiate. So the advancement of our work is that in previous work, the zinc oxide, like UV light has to be shined on it. But in our work, visible light can be shined because the band gap of the cuprous oxide nanoparticle is lesser than that of the zinc oxide, that is around 2.16 electron volt. So we have also done the characterization of the PMMA, which we have prepared. We have done the GPC, in which we can know the molecular weight The PDI, which is, yeah, this is a little bit more as expected, but this is the best we got till now. That is 1.9 PDI. We are trying to control it. And from the IR also, we can see the bands of carbonyl and CBr. And the absence of the C double bond C stretching, we can confirm that the PMMA has been synthesized. We have also done the 1H NMR. And this exactly, like we have also matched it from the reported PMMA. And from the alkyl peaks, we can conclude that the PMMA has been formed. So our aim was to demonstrate the photo-induced ATRP of MMA under visible light by using cuprous oxide nanoparticles. So the polymethyl methacrylate was characterized by IR and NMR, and its GPC was also done. So the advantage of this reaction is that it is a very simple reaction, no use of expensive compounds, and it is a very mild reaction conditions in which the polymerization is taking place. So we are trying to do the polymerization in a much more greener manner. So further the optimization study and the control over the PDI, and by also we are trying various other monomers to polymerize by this specific method. So this is going on in our lab. So lastly, I want to acknowledge the Shodh Fellowship who is funding me for my research work. Of course, I am very thankful to Professor Hemant Soni sir and his student Neelam Gupta. They provided me the cuprous oxide nanoparticles for this scheme. And of course, thank you for the organizing committee of Somaiya Vidya Vihar University to like giving me the opportunity to present this piece of work in front of like dignitaries like you, like all of you. And thank you so much for your kind attention.
Thank you, Sneha. Please wait here. Anyone question?
Firstly, can you hear me? Yeah. First of all, let me compliment you. Your presentation was very good. Okay.
Thank you,
so
sir.
Your clarity was very good, and I think keep it up. Okay, because it's very important. I very rarely see people with this kind of a clarity. Okay, good. The second is, you're taking a semiconductor, like a copper nanoparticle, and shining visible light, and putting in methyl methacrylate. Okay, just try one experiment.
Yes, sir.
Don't put any ATRP initiator. Okay. Just take methyl methacrylate, put the copper, nanoparticle semiconductor, shine light, see if it polymerizes.
Okay.
Okay.
Sir. Yeah.
Okay. I'm suspecting this is purely a photo-induced radical polymerization. Okay.
Okay.
And for that, I think the rest of it may not be important, because we know that in the presence of a photochemical initiation, methyl methacrylate will polymerize very easily. So it's a simple radical polymerization, and so you may not need any of those ATRP systems at all. It may be a simple photochemical radical polymerization.
Okay.
And I think your PDI tells me that it's probably that. Okay. Because 2 is close to 2. Okay, which is the most probable distribution. So try one control experiment. Okay, where you just take the semiconductor nanoparticle. Okay, and shine light on it and put methyl methacrylate.
Yeah. So like I just followed that report in which the ATRP. Yeah.
Try it.
Okay. Yeah. Of course, I will do.
You do a control, because if in the control you get no polymerization. Okay, then only I have to think, because your PDI is 2.
Yeah.
Okay. So I think you are getting a radical polymerization, but it is not a control radical. It is a simple radical polymerization which is giving you the most probable distribution. And we know, there are examples in literature where if you take light and methyl methacrylate, it will polymerize. Okay. And of course, one thing that you should check out there is, and this is a probability, is how well you have excluded oxygen in the system.
Yes, sir. Yeah, that is
because
one thing.
the reaction I'm telling will happen if the oxygen is present.
Okay.
Yeah. So But if you have absolutely deoxygenated everything and there is no trace of oxygen in the system, then only you can hopefully do the other one, which is the atom transfer radical polymerization. You know.
Okay.
But if you have little bit of an oxygen,
Then
you
also
may
you
end
go
up with a simple
radical,
radical polymerization, which is sensitized by the semiconductor nanoparticle.
Okay, sir. Yeah, thank you so much, sir, for your suggestion. Yes, sir. Yes, sir. Okay.
So there is a paper in Macromolecules. They did photopolymerization of MMA.
Okay.
Okay.
Okay,
So
sir, yeah.
you check that.
Yes, sir. Yeah, I will look into it, sir. Yeah, thank you so much, sir. Yeah. Yes, sir.
Any more question? Thank you very much.
Thank you.
With this, we are coming to the last presentation. Avinya from PhD student from ICT Mumbai.
Good evening, everyone. I'm Abhinaya. Today I'm going to present on the topic depolymerization of PET bottle waste and utilization of depolymerized products in coating applications. This is the flow of presentation. Due to the widespread application of polymers, waste management is becoming a threat to polymer industry. And as we all know, PET is one of the versatile plastics, and it is a noxious material, and its usage is increasing every day, and hence its waste. So the global demand of PET is increasing every day at a growth rate of 4%, and it is further increasing to 27.1 million tons by the year 2020 to 2025. It is going to just directly go. Previous slide. The fourth one. Okay. There are various methods of chemical recycling of PET, glycolysis, alcoholysis, hydrolysis, and etc. Here I am going to talk about glycolysis and aminolysis of PET. Next. So the main objective is to recycle PET bottle waste by sustainable environmental friendly method, glycolysis and aminolysis. Here I have used ethylene glycol and neopentyl glycolysis glycolytic agents, and amine 4,7,10 trioxo 113 tridecanamine. And further, to make use of this depolymerized products and value added applications in different coating applications. And the third objective was to reduce the use of solvent. Next. And firstly, for the glycolysis of PET, deep eutectic solvent was used as a catalyst, and for this I have prepared by mixing choline chloride and urea in a molar ratio of 1:2 for 2 to 4 hours, and the structure was confirmed by FTIR. Next. Depolymerization of PET using ethylene glycol and neopentyl glycol. PET to glycol ratio was taken on molar basis 1:3 and with 5% dipydactic solvent as a catalyst. And the reaction was carried out at 200 plus or minus 5 time for 2 hours. Next. And the depolymerized product was further used for the synthesis of polyester polyol with acid to OH ratio 1:1.2. For this, FastCat 4100 was used as a catalyst and temperature around 160. Xylene was used as an azeotropic solvent. And this was the structure conformation. Next. And the polyol was used, cured with aliphatic polyisobcyanate using xylene and methylethyl ketone as a solvent, which was cured at 140 degree for 15 to 20 minutes. These are the mechanical chemical properties of the polyurethane coating. So actually the mechanical properties are not, the mechanical properties for both the coatings were comparable to the commercial coatings, wherein we have done impact resistance, flexibility, etc. And then for the chemical resistance, acid resistance was good, and in case of alkali resistance there was loss of gloss, and over a period of time the film was removed. This could be due to the saponification of the ester linkage. And thermal properties were also analyzed. The TG values of both the coatings were around -8 and -6. This could be due to the high flexibility of the film. The dimer acid and adipic acid used in the synthesis of polyester polyol is responsible. And this next. And this is the TGA analysis. And salt spray analysis was carried out for 500 hours with 3.5 NaCl, and this is before exposure and after exposure. And next, PET was used for used in aminolysis using this amine, and this is the reaction conditions. And it was confirmed. This is structure conformation. And the depolymerized product was used as a hardener for both epoxy coating and polyurea coating. These are the curing conditions. It was for epoxy curing, it was cured at 140 degree using epoxy YD128, and for polyurea at 150 degree for 30 minutes. So some of the properties are not visible, mechanical and chemical properties. This is DSC. This is the thermal properties analysis, and the salt spray analysis was carried out for 500 hours for epoxy coating. This is the comparison. Next. Many of the properties are not coming actually. This is the TGA graph. The TGA in case of both epoxy and polyurea coating is high compared to the conventional coatings. This could be due to the aromatic content in the structure. This is the TGA analysis. Salt spray for both epoxy and polyurea coating. And further, the aminolyzed product was used for the synthesis of UV oligomer. Firstly, it was reacted with bio-based itaconic acid and then with HEMA, and the UV oligomeric product was used for curing. These are the analysis. And it was used in combination with epoxy, commercial epoxy acrylate up to 50%, and reactive diluent TMPDA was used 25, and photoinitiator RIGAQ 651. These are the properties of the coatings, chemical. Again, further thermal properties were analyzed for all the coatings with comparison. All the coatings showed good coating performance, almost comparable to the commercial coatings. And the main objective is to reduce the cost, as we have not done any separation. The time and cost could be reduced. And lastly, raw material recovery. I would like to acknowledge my research supervisor, Dr. Anaga Subnis, my HOD from ICT, family, friends, and lab mates. And thank you for this wonderful opportunity.
Anyone having question?
When you make presentation, don't make so many animated slides.
Sir, actually the number of slides are more in those cases. So
And
I
another
wanted
thing,
to put all the properties in a
yeah,
single
another thing in the slide, you don't put so many colors. It looks odd. Now, the professional presentation, put colorless thing. Or if you want to put only one single color, light color.
Okay.
Otherwise, you see your many things, many figures, and these things are not visible properly.
Okay.
Yeah. So, what is your objective of this work you have presented? What was the objective, and how much you carried out?
My first aim is to recycle PET waste and its value added it's further application and value added.
So, why did you use this DES?
Sorry?
Why did you use DES? You have used DES.
Yes, sir. It is a catalyst for the glycolysis of PET, deep eutectic solvent. It is a analog of ionic liquid. So it's a green catalyst. So it was used for the.
And how much you are adding this DES?
5-8%.
And what is the full name of DES?
Deep eutectic solvent. Deep eutectic solvent.
Deep eutectic solvent, yeah. And how did you get that composition that it will lead to DES? How could you get it?
Sir, actually there are 4 different types of DES. Here I have used choline chloride and urea mixture. Basically hydrogen bonding is happening.
Okay. Good.
What is the maximum percentage of recycling to useful products? For example, what is you have used maybe 100 grams, take 100 grams. Out of this 100 grams, how much useful products you would, how much gram useful product, approximately?
Like here I am using
any case.
So the properties may not be as good as.
No, forget about it. How much you have recycled? Put to use, how much?
Here I am using.
No.
We have not carried out the separation. So we have used total product plus byproduct.
So you mean the efficiency or?
Efficiency.
Sir, actually here the main aim is to reduce the use of solvent. So we have not gone up to more of glycolytic or aminolytic agent.
That is the point, efficiency, but recycling efficiency.
Yeah.
So you have not done.
No, we have not, because we have not done any separation. So the unreacted ethylene glycol or whatever glycols we have used will remain in the system.
You will do it, no?
Sorry?
Ultimately you have to do that, no?
Sir, as we have used the whole product for the end application, we can't calculate the yield, right?
No,
When we do the separate,
yes. Whole product is used for the end application.
Yes, sir.
It's 100%.
Yes. Yes, sir. It is 100%. Yes. Yes, sir.
Anyway, look into that aspect.
Sorry. We have used the whole product. Whatever product we have got, for example, 100 grams, so we have used the 100 gram of product for the end application.
In case of glycolysis, I have combined with neopentyl glycol, but in case of aminolysis, it was only amine used for the coating.
Okay.
Yes, sir.
So, for example, if aminolysis is done, we have calculated the amine value as well as the hydroxyl value. On the basis of amine value and hydroxyl
value, we have calculated how much. Yes, sir. Yes. Yes. Yes.
which is organic compound. You have a polyester polyol.
Yes.
And of course, you are now adding neopentyl glycol also to
Yes.
that. So how do you get the hydroxyl stoichiometry?
So of course we will get the hydroxyl value for unreacted ethylene glycol or neopentyl glycol and the glycolized product, and we have on the basis of hydroxyl value we have calculated the amount of
isocyanate. The
isocyanate.
hydroxyl value, the mixture or individually?
No, in the
sir.
mixture.
Mixture only.
That's not accurate because the molecular weights are different.
Yes, sir.
Okay.
Yes, sir.
So how can you do that? So how did you? The polyester polyol has a higher molecular weight.
Yes.
Whereas ethylene glycol and neopentyl glycol are lower molecular
Yes.
weight. So how did you balance the hydroxyl in terms of equivalence? Because the molecular weights are different. You get my question?
Yes, sir. Yes, sir. I got your question.
So ideally what you should have done is that separated the ethylene glycol. Okay. And then taken the hydroxyl equivalent, because then you must know the number average molecular weight of the polyester polyol, then do the hydroxyl equivalent, then you will know the real equivalent of hydroxyl group. Understand?
Got your
Because
point,
for the
sir.
hydroxyl number and the molecular weight. So you must do the molecular weight measurement of the oligomer. Then ethylene glycol has to be separated at that time. Otherwise your averages will get mixed up, you know, because your average molecular weight, if I don't know the molecular weight, I cannot determine the end group concentration.
Yes, sir. Yes, sir.
Sir, actually the separation work has already.
The other component now.
Yes, yes, sir.
Just add the amount of isocyanate required for the hydroxyl.
Yes.
Well, I don't know.
So that means it doesn't matter. You're getting a mixture. Some places just ethylene glycol is important.
Yeah, but then what is that?
We know how much OH moves per unit gram.
Yes.
Just add the amount of isocyanate required. React to.
So it's a kind of a combined.
Correct. Per gram, then you don't need the molecular weight because you were weighing the.
If it's per gram, no, but I was wondering how they are.
Correct, but what you're doing here is the objective is stated to prevent, to avoid any separation. You want to make it simple. Maybe just.
One general question. What is the percentage of PET recycled in our country that is being produced? So you said some million tons is produced.
Yeah.
How much is recycled? Or is there any statistics available of the...
Statistics is
It
available.
is there, but we are not sure.
Actually, I'm not sure at this time, but the maximum of polymer which is recycled nowadays is the PET. So yes, this is what I know.
Which company recycle it? Is there any company doing that?
Yes, sir. BSF I know. Beside BSF, many companies are into it, but BSF.
So what is the major method of recycling?
So chemical recycling they are doing.
Is bringing back the glycols.
Yes, sir.
I mean, monomers are taken by.
Yes, yes, sir. Yes, sir. Monomer recovery is happening.
Okay.
GPC you are saying, sir, or GC? Okay. Yes. So we can go for that. to carry out the separation for that. Yes, sir. Yes, yes, sir. Thank you, sir.
Thank you very much. Thank you, Shubhendu, Nidhi, Rani, Ananya, Sneha, Avinaya, for your presentation. I am really, they have presented from very recent work, lithium battery separator, sustainability, and then using this ACRT and photopolymerization nanoparticle for as a catalyst, and here it is hernia mesh and everything. I request all of you to clap your hand to give them an encouragement so that they come again for the presentation in such forum. Thank you very much.
See, I said it long back. I said it yesterday. Anyway, we still have a very pleasant job yet to finish. Ma'am, please be seated. I would invite Dr. Shivram to come on the stage, and individually we will call one by one people to give away the shawl to these young, dynamic researchers so that they can remember this eventful day. So can I have the shawl, please? So, sir, here you can start from the first speaker. Yes, Shubhendu. Please come forward. You just stand here. তুমি কি আমি কল আউট করব? ঠিক আছে। হ্যাঁ। Yes. Let's join hands and care for a photograph. Yes. Thank you, sir. Now I would ask our Vice Chancellor, sir, to come on the dais. You, sir, be there. Sir, be there. But, yes. Professor Pillai will be presenting the shawl to Nidhi. Nidhi, yes. Yes. Very nice. I would now like to invite Professor S. Ramakrishnan to come on the stage. Sir, thank you. And he would be presenting to Rani Gupta. Very nice. Just for a photograph. Yes. I would now request Dr. Virendra Kumar Gupta to kindly come on the stage and present a shawl to Ananya Rajamanur. Thank you, sir, to do the honors.
I also got the same. Probably she gets a better one.
Very nice, sir. Thank you so much. I would request Dr. Professor Anil Kumar ji to come on the stage to present a shawl to Sneha Soli. Thank you, sir, and good luck, Sneha. Oh, and I would request Dr. Benny K. George to kindly come on the stage to present the shawl to Abhinaya, if I have spelled Abhinaya. Okay.
If he gets up before you, then what happens?
And what's her name?
What is her name?
Okay. No, she will get a separate one.
Definitely.
They will
I'm
not
saying.
share. And I will request now Professor Dr. Benny George to come on the stage to give away a shawl to Mrinalini. Yes. So all the students answered the questions very well and spoke very well, and let us give them a very big hand. And let this day not be the last presentation. This is just the beginning of their journey, and we wish them good luck for their scientific endeavor.
Whoever wants to join with them,
Vandana, please come. Daddy, please, sir.
please come.
Abdani, sir.
This is a rare occasion.
Kulkarni, sir, please come. Vadgamkar, sir, please. Vadgamkar, sir, I would request you to just stay back. We still haven't done the honors for him. He was doing the poster evaluation. So he has chaired that session. So, sir, just be seated. And to do this, we will ask Chandana madam to present the shawl and the memento. Just be seated. I'll get there.
Are we going to announce the poster hours?
Yes, after this. So, thank you, ma'am. And thank you, sir, for taking all the trouble to go through the posters and
इधर से जाती है.
to come on this side and that side. So, may I have your attention, please? I would invite Mr. Satyen Daga to come on the stage, Dr. Virendra Kumar Gupta, yes, Professor S. Ramakrishnan, Dr. Shivram, Dr. Vandana Jamdar, and Professor Pillai to come kindly on the stage. We are now closing this two-day event. And we will be giving away the poster award. Yeah. Yes, kindly sit.
Once they settle, once they settle.
Are there enough seats? So one by one. So I'll just announce one by one.
No. First, you said now we are announcing the best poster award. Then we will award for awarding. First, you call best poster award by Adhiti. Adhiti Jawan. Adhiti Jawan for the best poster award in the Asian Poly. First, Adhiti Jawan. Now it is American Chemical Society best poster award. First you call Adhiti Jawan and you introduce her the best poster awardee of Asian Polymer Association International Important on this. And she tells her to speak few words. Okay.
So you took over my So we are coming to the close of the program, and for this, we have the pleasant job of announcing the American Chemical Society Poster Award. But before that, I would like to invite our own student, Ms. Aditi Chavan, to come on the stage. She is the recipient of Asian Polymer Association International E-Conference Award, which happened very recently. So we would like her to say a few words about her experience, and then we would announce the Best Poster Award for this particular symposium. Yes, Aditi, please. So let us give her a big hand. She's the recipient of the award of the International Conference. Yes, Aditi.
Good evening, everyone. So the journey for the research work we are doing right now, I'm doing my research work under the mentorship of Dr. Anand D. Kulkarni. We were given to write a research proposal as well as a term paper for our third semester evaluation. But Anand sir was very adamant that we are going to do a full-length paper anyhow. Like he was like, we don't have to do a review paper. We can do a term paper. We can do a research paper, a full-length research paper. And it was his belief in me, and it was really encouraging after I got the poster award. But we were not really aiming for it. We just even today we presented a poster award. We expected some comments from all the dignitaries so that we can obviously develop a very better paper. We needed comments and criticism, a constructive criticism from every one of you. So it was a really encouraging thing to win the award, but it was an amazing experience to present something in an international conference, and that was because of Sir, and obviously Somaya Vidya Vihar for giving us this platform. Thank you.
Great job.
Okay. And she will be giving away the award to the best poster, to the this American Chemical Society Poster Award to one by one. I will be calling out the name. Well, the order doesn't mean that who is best. All are good, and they deserve it equally. So the first one goes to Shubhendu Samanta. Please come. And and receive the prize from Aditi. The next candidate is Ms. Rani Gupta. Please come and receive your prize or award, I should say. She's there, she's there. Very good. The third person is Mr. Yogesh P. Patel. Are you there in the auditorium? Please come. Patil, okay. I'm sorry I pronounced your name wrongly. Mr. Yogesh P. Patel. Patil, sorry. Okay, good, good. Very nice. The next one is Ms. Priyanka Dobaria. Priyanka, are you here? Please come. And as I said, don't go by the order. We have not followed either alphabetically. All are good. Yes. The next one is Ms. Debarati Maiti. Please come and receive your award. The next one is Adebayo Isaac Olosho. I do not know whether I pronounced your name correctly, but you know I called out somebody. Okay, thank you for coming and joining us. Very nice. The next one is Miss Sonali Kamle. Is she here? Sonali is here? Yes, please come. She is our own student. A big hand to Sonali. And last but not the least, it is Mr. Karan Salve, again from Somaya College. Heartiest congratulations to all the recipient of the American Chemical Society. Thank you, Aditi, for doing away the honors. And let me tell you, the jury for the poster awards were Professor Vadgaonkar, Dr. Benny K. George, Dr. Druman, Dr. Ghosh from Solvay Chemicals. So they have done an excellent job. Let us give them a big hand and thank them from the bottom of our heart. So with this, we come to an end of this two-day symposium. Oh, so the vote of thanks will be given away by none other than our coordinator, course coordinator, Dr. Vandana Jamdar.
It's my privilege, honor to give today the vote of thanks for this two-day symposium. So good evening, all of you, dignitaries on the dais, as well as all my colleagues.
If they have one or two persons, some impressions on the content, that is usually. Some comment, some observation, please.
Okay. As VC sir said, if you want to have any comment or impression about the comment,
Observations on the conference. Anybody, students, participants.
So
anybody.
please come on the dais or share from that. Yes, please. Please give them the mic. We would like to hear from all of you. Students? Industrial delegates? Anyone, please? We just want your 1 or 2 lines about our symposium, your impression about the symposium. Sir, we will get the feedback from them.
That's all. Somebody's coming.
Yeah. Okay.
Take some initiation time.
Thank you, Soumya, Vidya Vihar University. After college, this is my first presentation as an industry delegate. So I'm really thankful. Even I'm thankful to Aditya Billa to giving me an opportunity to participate in such very, very productive, very knowledgeable symposium in front of so many legend, you can say, dignitaries here. I met everyone first time in my life and I'm very much happy. As sir told yesterday, one of the sir told yesterday कि अभी हम जब 100th birthday पे मिलेंगे शिवराम sir के, so maybe I'm one of them and I will say हाँ मैं भी उनको 25 साल पहले मिली थी.
We will all be there.
Yes, we will all be there. नहीं मैं मतलब मैं आऊँगी ऐसे. I will be definitely part of it and I will say हाँ मैं भी sir से first time मिली थी सौम्या Vidya Vihar and it was a good interaction. I have a photo with sir as well. So I'm very much happy and thankful to Soumya Vidya Vihar to arrange such a good conference. Thank you so much. Thank you all of you, sir. Thank you, sir. Thank you, sir.
Yeah, please come.
I would like to say a very big thank you.
Yeah, you can come.
Tell us from which country you are.
Okay. My name is Adebayo Isaac Olosho. I'm from Nigeria. Yes, right now, I'm a TOAS CSIR fellow at NCL in Puri. And I would like to thank the organizer of this program, Professor. Thank you. And also, our highly distinguished researcher. Actually, when I read this autobiography, I was intimidated. And I was feeling like, am I going to rise to this kind of height he has gone to? And listening to what motivated him along his career path, I feel it's a possibility for some of us that are very young like this. And it doesn't matter whether you have few resources or not. What is important is the ideas you have, and if you believe in the idea, then you will have people who will support you. So thank you very much for giving us that example to look up to. And I really want to thank the evaluation committee for considering my poster. I wasn't really expecting the award. Thank you, sir. And thank you for every speaker. Thank you to the organizers.
How long
thank
have
you.
you been in India?
I came to India last August.
And how long will you be here?
I'll be here till July 23. Okay, yes. So I'm in my 4th year PhD, registered in my country. So I came here on exchange program. Yes.
Yeah,
Thank you.
very nice. Thank you very much. Anyone else? So, yeah. Okay, sir. Thank you very much. So, good evening, everyone. Behalf of Organizing Committee and Department of Polymer Science, SK Somaiya College, Somaiya Vidya Vihar University, I take this opportunity to express my gratitude to all of them who has contributed and supported our event to make it as a grand success. Yes, we would like to thank our Chancellor, Mr. Samir Somaiya, who is our inspiration and motivation. Our Vice Chancellor, Professor VNR Pillai, our rock support. Our mentor, Dr. S. Sivaram, his constant guidance is a boon for all of us, and every interaction with him is an enriching experience for all of us. Yes, none other than our director, CA Monica Lodha, for facilitating all the required support for this event. We also would like to thank all the eminent speakers and chairs from industry and academia. We will remain thankful to Dr. Prashant Kumar, Dean SIRAC, for his prompt support for this event. Also, I take this opportunity to thank our sponsors for this event, Pidilite Industries, Praj Industries, Reliance Industries, Ghada Chemicals Limited, American Chemical Society, Royal Society of Chemistry, and look forward the same in near future also. Yes, I will take this opportunity to greet or I'm thankful to Dr. Ramakrishnan, President, Society of Polymer Science India, for giving an opportunity to host such a grand event on the occasion of the Sivaram Sir's 75th birthday celebration in collaboration with SPSI. Sir, we are thankful to you. Of course, this event would not be possible without our support system, like IT support. Special mention to Mr. Milind Khedekar, Mr. Amaya Rani, and Firoza for the website. So thank you. Of course, and our vendors for dedicated support, Sarthak for audio systems, then Mr. Vipul for videography, Mr. Prakash Vaidande, you are here, for photography, and of course, Cosmos Caterer for all the delicacies and prompt and hygienic service for these 2 days. Perfect Solutions, Mr. Jay, who has made available any stationery as and when required on our one call. And also I would like to thank Awaz Company, Mr. Jiten Merchant, for their wonderful arrangement, which you are seeing. I also would like to thank Ms. Babita Krishnan, Madam, for making all the desired approvals for this event. Project Office, Mr. Gupta, for electricity provision for our dinner, which we had yesterday evening. Our security, who helped us to make both entry and exit smooth for all the invited speakers, guests, and participants. Yes, none other than our PR team, Pushpendra sir and Muskan Thakur, making this event as a brand success. And of course, the engineering auditorium support team for making everything available on time as and when required. Then special thanks to VC office team, special mention to Richa Bhutelo and Aparna Mandalik for their help and as and when required. They were just one call away every time. And I take this opportunity, of course, to thank my department colleagues, Dr. Padma S. Vankar, Dr. Vaijayanti Ghase, Dr. Dali Davis, Dr. C.V. Avadhani, Dr. A.D. Kulkarni for their team efforts, and look forward the same in near future also. Yes, I am thankful to my department support system, Ms. Madhuri and Mr. Tapal. They were with us for last 2 days continuously. Not but the least, I am thankful to all my dear students, MSc Polymer Science, for volunteering.
Stand up, MSc Polymer Science.
Yes. For their prompt volunteering for this 2-day event, and all the participants for their proactive participation. Please excuse me if I have missed anyone unknowingly. On this note, I take a leave. We will definitely meet you all in many more events like this in future. Yeah, yes, in Somaiya Vidya Vihar University. Once again, thank you all. Stay safe. Thank you. Thank you very much.
Those who are here, if Vaidande can make a group photo.
Can we
Those
give
who
a
are
big
here.
hand to the organizers.
Yes.
Very good. All these
Really
wonderful young faculty members of the Somaya Vidyavihar University, the students of the master's program, and of course, without the Vice Chancellor, nothing would happen. So I think his great
He was
support-
the driving force, sir. So we should say hats off to sir.
Always.
Yes. Thank you, sir,
Thank you.
for all the words of appreciation. And thank you, audience, for being there with us for the last 2 days. And have a safe time. Thank you very much.